Okay, well, here now. There are 30 cows in a field and 28 chickens. How many didn't?
10.
30 cows in the field, 20 of them ate chickens. How many didn't? 10. 10 cows did not, in fact, eat chickens. All right, what a fun riddle. I know you're all going to go home and tell that one to your friends and family. Okay, so folks, here we go, my math lab. So folks, when you go into my math lab, and I definitely want to model a little bit of this because a couple of you told me that you had some challenges with my math lab. So let's look at it together. You go into 218, so I'm clicking on 218. And the only thing you really need to click on in here is the tab that says homework. So right over there on the left, it says homework. You click on it. And then here's our chapters that we're doing for this class. Chapter 1, 2, 17, and then chapters 3, 4, 5, and then I'll put in later on chapters 7, 8, 9. So I'm going to go ahead and click on chapter 1, which was due tonight. And here you go. You've got 23 questions. I think that's reasonable. I know that some of these questions are a little longer than others, but not too terrible. So if I go ahead and click on number 1, question 1 here, it takes a second to load. Here we go. So this first question, find the slope of the line through the following pairs of points. So we're going to do the slope from -4, 1 to 4. So first of all, is the slope, does it exist or is it undefined? It's not undefined. So we would go ahead and calculate the line, which is, I think, 1/8. So let's try it out. Type it as a simplified fraction. So I'm going to use my fraction button and do 1/8. And let's just see how I did in 2 seconds. Oh my gosh. Okay, so it was 1/8. So we're done with that question. We click on the next one. Here we go. All right. Now find the slope of the line through this one. So what about this one? Is this slope defined or undefined? What's a quick thing you could do to see if it's horizontal or vertical? In your mind or on paper, you could graph it, right? Because it's 2, 6 and 2, 5. And in your mind or on paper, you can look at that and say, oh, those 2 points are stacked right on top of each other. So the slope is undefined. So then I would go ahead and click on undefined. And again, we're on our way. Nice work. Now, eventually, you're going to get to a problem that you might not know how to do off the top of your head. So let me click ahead here. Maybe I'll go to question 10. So here it says, write an equation in standard form for the line described through 8, 9, perpendicular to this one. Okay. Now, like this particular question, it wants the formula in standard form. And now that I'm looking at that, it occurs to me we didn't necessarily do that last week.
Yeah, we did.
Did we? We wrote it in standard form?
No.
I don't know that we switched it to standard form.
But I
So-
think they're just similar.
What?
But I think they're just similar.
Yeah, they are fairly similar, and it's a simple matter that you can do it. But let's just think, what if you get to a problem that we didn't cover exactly in class? Well, then you'd go over here to question help, and the first thing you could do is click help me solve this. And that will literally walk you through the problem line by line by line. And then when you're done, they're going to have to give you a different problem because they just showed you how to do that one. Or you could go to question help and say view an example. Then it will show you a different problem, and it'll walk you through it line by line by line until you get the whole problem. Or you could always just go to the textbook, and it will show you the example problem that they had in the book. And sometimes there's a video. Looking at this particular problem, it doesn't look like there's a video for it. Or finally, you can click Ask My Instructor. And when you click on that, it's going to send an email right to me, and it will even show me the problem, so you don't have to tell me what the problem is. But I do want you to tell me what you did. Like, hi, Mr. G, I tried the answer, like 4x plus 2y equals -10, but it was wrong, or something like that. At least tell me something. Don't just say help. Tell me what you did. And then you send it to me, and I'll write you back within hopefully a couple of hours. Okay, so now all that said, let's just take a look now at all my problems. You see now this is the list of all the problems we have for homework. I've got 2 green check marks next to the 2 I've finished, and I've got a red X next to the one I didn't do yet. You can keep on trying that one as many times as you like. There's no limit. You can just keep on trying it, and eventually you can get the credit for it. Okay, Loretta.
Do you respond to emails on the weekends as well?
Yeah. I pretty much, I will always respond to emails before I go to bed at night. Because I don't want you to get, if someone emails me, especially at like 9 o'clock at night, I try to email right back because they're kind of stuck waiting until I email them back. So I try to email back very quickly. Okay, so those are our questions. Was there any from chapter 1 you'd like to see? Does anybody remember one in particular that you'd like to see?
I had trouble on this one to see.
This one right here?
Yeah, the graphing part. I knew what the answer was, but I was trying to
How to graph it, like the different ways.
Yeah, so yeah, you got a lot of buttons here, don't you? And you kind of have to play around. Now it says click on the graph, choose a tool in the palette, and follow the instructions to create your graph. So I know that my graph is y equals x minus 2, so the y-intercept is -2, and my slope is 1, which means 1 over 1, which is up 1, right 1, up 1, right 1. So I'm going to choose the line tool, and I'm going to put my first point on the y-intercept, which is -2. And then at that point, all I need to do is put one more point to nail down what my graph should look like. So I'm going to choose a point that's up 1, right 1, up 1, right 1, up 1, right 1. I can choose any point up 1, right 1, because that will have a slope of 1. And at that point, I believe I'm done. I'm going to click Save. There's my graph. I'm going to say Check Answer. And it says Nice work. So just in case you wanted to see another one of those, let's try graphing. Oh, it already showed me another one. Here. Let's say you wanted to graph this line. Again, you'd have to show work first. You'd have to rewrite this as y equals mx plus b. So you solve your equation. Here, I'll go ahead and do that real quick. You've got the equation x minus y equals 6. That's my trash can until later, but I'll just throw things over there. Okay, so now I have to go ahead and move the x over to the right-hand side. Then I have -1y equals -1x plus 6. What did I just do with my x and y variable? Yeah, I put the 1 in there because it's helpful to have actual numbers to deal with. Anytime you have a variable with no number, you know it's a 1. So now I divide everything by -1. I divide it by -1. And now I have y equals negative over negative is positive 1 over 1x minus 6. So now let's go ahead and go back in here. If I wanted to do it correctly, whoop, click to enlarge graph. I like that enlarge window there. I would choose my line, and I would do the y-intercept of -6, and then I would do a slope of, up 1, right 1 again. So there it is, and that's my line. However, just to show you a couple other tools, there we go. Boy, I really like how it says click enlarge to graph. You can also do a parabola this way. So you nail down the first point, and then you choose whatever other point to make it a parabola. There's other tools in there too, like you could do an absolute value graph. So again, you get your graph. You can make a circle in there by putting the center and then the outer rim point. And you can go through and you can clear everything, and you can start over. So let's see if we did it. Was it -6 with a slope of up 1, right 1? Save, enter. Oh, goody gumdrops, it was. Okay, great. I'm glad we're doing this together. Shemaya, what other? Do you remember any particular questions?
I only got to like 11 because I had trouble with the graphing part because I was trying to graph both coordinates, but there was one. I was trying to put 1 and -3, and if it was x was 1, then I was trying to put the whole.
Okay, well, do you see how the graph works now? Okay. What about the rest of you folks? Any questions from the homework that you remember off the top of your head? Okay, well, let's start a practice together. And that practice will be that when we come into class, the first thing we'll do is we'll do our quick conceptual review, talk to each other about concepts. And then I'll pull up my math lab and do any problems that you want, with a maximum of like 3 problems. We don't want to spend too much time doing it. But I could show you how the trickier ones work, okay? Because I'm trusting that you're already will have clicked, show me how to do this, show me another example, watch the video, do all that. But if all those resources don't help you, then I'm going to stand here and make sure that you understand.
Where can I find videos?
The videos, depending on the question, like this question right here, it doesn't have a video.
Like I was able to walk through each of the problems, but I was able to walk through each problem fine. I was getting the right answer, but the way I was inputted in the boxes, it was literally telling me I was wrong, and literally it was the same answer. But come to find out, it's the way like when it's negative with that little box, like the 2 little boxes, you have to center it right for it to be correct.
Oh wow! So it's very technical.
Yeah. Okay. So I kept doing it over and over, and I'm like, I don't know.
Oh man, I'm sorry. So again, email me, because folks, I don't want you to have any frustration in terms of knowing how the system works. You just email me and I'll show you how to do it. Okay. Well, let's see here. I think that's it then for this particular section, unless somebody else had another question. Maybe that's it. So yeah, folks, know that we can always start class by doing a couple of these together. Now, remember, there's no quizzes and tests. So if you click on quizzes and tests, there's all sorts of things in here. You don't have to do that stuff. You don't have to do any of that. You're only clicking on the homework link, and you're only doing the chapters that we're actually doing in class. All right. Well, I think that's it for that. Anyone have any other questions you'd like to ask? All right, there we go. Okay. Well, folks, today we're doing chapter 2. So everybody take a look at the packet I gave you. It says Introduction to Systems of Equations. This is our warm-up. This is our brief overview, and I mean brief, of everything you've ever learned about solving systems of equations before today. Because,
Mr. G?
Yeah.
Which packet says that?
Yeah, we don't have it.
It says one of them says chapter 2 notes, the other one
sorry,
is find the
the
slope.
front page thing just says find the slope, and what we're going to do is we're just going to go ahead and skip in until you see that graph. There it is. So it's there. Yeah. We're not going to do the whole first part of the packet because we kind of already did it last week, but we are going to definitely review this. Thank you, Loretta. And everybody, please, if I'm doing something and it makes no sense, you throw something at me. I'm just kidding. Don't do that. One time a student did throw something at me. It was in high school. I said, throw something at me. They did. They threw a pencil and it almost hit me in the eye. It was insane. So please, but if you're going to throw money at me, that's fine. Okay. So, I'm going to go ahead and move this over so that it's on my board. That way I can actually draw on it if I want to. I believe I fixed it so I can. Ooh, that looks good. All right. Now, I briefly showed this to you last time right as you all were leaving. Where's my eraser? Did I leave an eraser on somebody's desk? Ah, there it is. I did, and my markers. So today we're talking about systems, folks. First of all, everybody circle the word system. What does system mean? Yeah, what does system mean? Yeah, 2 or more, that's it. It just means 2 or more. It means that you're putting 2 or more graphs on the same coordinate axes. So you're looking at 2 graphs at the same time. By the way, does everyone have this? I should really check. Yeah, everybody has it. Nick, you have it too? Okay. All right. So, and then what do we mean to solve it? What do we mean by solve a system? To solve a system, what are we looking for?
Where they intersect.
Where they intersect. Exactly. Point of intersection. So, for the whole rest of today, when we're talking about solving a system, visually, that means finding where they intersect. Now, everybody go ahead and cross out this wrong slope of 1/3. It's actually supposed to be the equation of y equals 3 over 1x minus 3. And then my other equation is y equals negative 1 over 2x plus 4. So, if I walked up to you and I said, hey, here's a system, solve it. Solve this system. It means we're going to graph both of these on the same graph. So my first line has a y-intercept of negative 3. And then the slope is going up 3, right 1, up 3, right 1. So I go up 3, right 1, up 3, right 1, up 3, right 1. And there's my first line. And then we would graph our second equation, which has a y-intercept of 4. So there's my y-intercept of 4. And this one has a slope of negative 1 over 2. So that's down 1, right 2, down 1, right 2, down 1, right 2. So I go down 1, right 2, down 1, right 2, or up 1, left 2, and there's my other line. Now, graphing is very simple and straightforward, and it's nice because you can visually see the answer. What's the answer?
2, 3.
Yeah, 2, 3 is the solution to this system of equations. Well, the thing is, you don't always have the luxury to do a graph, and even if you...
Get really big.
What's that, Loretta?
The numbers could get really big.
Yeah, the numbers could get really big. It might not be, they might not intersect right on a grid, right on the grid corner. You might need a graphing calculator to do it. There's all sorts of reasons why graphing is not the ideal way of doing it. Especially, for instance, if you have 1,000 problems that you have to solve today, you don't want to sit there and draw 1,000 graphs. You want to type it all into the computer and let the computer solve it for you. And the computer is going to do it using equations and algorithms, and that's what we're going to learn. We're going to learn to think like a computer. But this visually gives us a nice idea of what we're doing. So, yes, this is the point of intersection, but what now will the coordinate 2, 3 do to these equations? If I plug 2, 3 into this equation, what will happen? So we take 2 and plug it in for x, and we take 3 and plug it in for y. What will happen? It'll be true, right? So we plug 3 in for y, we plug 2 in for x, and we get 3 equals, 3 times 2 is 6, 6 minus 3 is 3. We get a true statement. This is, at heart, conceptually, what we're talking about. A solution to a system will make both equations true. And that's mathematically what we're going to do with our algorithms and our equations. We're looking for a pair of numbers to plug into both equations that will make both equations true. What happens if I plug 2, 3 into this equation? I plug 3 in for y, I plug 2 in for x, and what happens there? Half of 2 is 1, but it's a -1, and so -1 plus 4 is 3. So that's our mathematical definition, okay? The visual definition of a solution of systems of equations is the point of intersection. The mathematical definition of a system of equations is the coordinate that makes both equations true. So you might want to write that down. So visually, in fact, I'm going to put it over here. Solve a system. When someone says that to you, you can either think of the definition visually. So visually, it's point of intersection. But mathematically, it's the coordinate that makes both equations true. The beauty of this definition is that you always know if you have the right answer or not, right? If you claim that the solution to that system of equations is a particular coordinate, I should then be able to take your coordinate, plug it into both equations, and see that both equations are true. And if I plug your coordinate into both equations and one of them turns out to be false, then you did not have a solution after all. So that is at heart what we're doing today. What we're going to do right now is look at a wide variety of methods that you have used to solve systems in the past. And by past, I mean far past. These are methods that you were using in high school. In probably 9th grade, 10th grade, 11th grade, and 12th grade, you were doing some of these methods. Now I think that's, oh no, I do have a couple more graphs to do, so I'll leave that up there. So on the next page, folks, go ahead and flip the page. Yeah, Carmen?
Do you have to memorize this?
Well, the translation, sorry, I didn't write that down. The translation is simply what I just put over there on the right.
Oh.
That to solve a system visually, it's the point of intersection, and mathematically, it's the coordinate that makes both equations true. And yes, Carmen, you have to memorize that for the rest of your life. Somebody walks up to you in 50 years, and they say, hey, what's the solution to a system? You should be able to say, oh, it's the point of intersection. You know, it's the point of intersection. Okay, so what does it mean to solve a system of linear equations on the next page? You don't have to write it down again. It means to find the point of intersection or to find the coordinate that makes both equations true. So you don't have to write that down because we just said it. How many solutions can a system of equations have? That first one only had one point of intersection. So how many solutions, i.e. points of intersections, how many points of intersections can there be? How many could you have?
There's 3 different ones, like, where they have a unique solution, where there's, I think, no solution when they're parallel, and then where there's infinite because they're on the same line.
Yeah, that's correct. So I'm going to come right back to you, Shmaya. The first possibility is that you have one point of intersection because the 2 lines intersect once. So that's one solution. The other possibility is that the lines are parallel. And because they are parallel, you have no solutions. Another possibility is that the lines are overlapping. And because they are overlapping, how many times do they intersect? How many times do they intersect?
All the time.
Yeah, infinitely many times. So there are 3 distinct possibilities, and that is correct. There are 3 distinct possible solutions that you can find to a system. Either a single point of intersection, which is simply the coordinate x, y. You'll just say, hey, there you go, that's the solution. Or no solutions at all because the lines don't intersect, or infinitely many solutions because the lines overlap. Now, all of this assumes that our system is made of straight lines. What if our system is made of lines that aren't straight? How many solutions could you have? Like, for instance, what if my system was actually a parabola and a circle? How many solutions are there?
2.
Yeah, 2, where the parabola intersects the circle. So if you allow yourself to consider other types of shapes other than straight lines, you could have a variety of different types of solutions. It really just depends on what objects you're talking about. But again, visually, this is very helpful to remember. A solution is a point of intersection. And graphically, that's what you're looking for, is the point of intersection. Mathematically, what you're looking for, though, is that anytime you claim that that's a point of intersection, you better be able to take that coordinate, plug it into both equations, and make sure that they're both true. Because otherwise, your graph is maybe just wrong. Your graph could be wrong. Okay, and then the last question, which I can't see. What kinds of solutions can a system of linear equations have? Well, those are the kinds. It was either intersecting, parallel, or overlapping. So intersecting, parallel, overlapping. That's all you would say. Now, the other thing that makes this class interesting is that we will go beyond 2 dimensions. So we won't just be looking at a 2-dimensional graph, we'll be looking at a 3-dimensional graph. And when you have a 3-dimensional graph, you're looking at 3 lines in space and wondering where do all 3 lines intersect. And that's tough to visualize, but how can we visualize that? Maybe with my markers here? This is a terrible, but can you just pretend that all 3 of these markers are intersecting at one point in space? So you could have 3 lines all intersecting at one point. So that's also what we're looking at, is 3-dimensional space, 4-dimensional space, 5-dimensional space, any dimensional space. Okay, so given that this is the concept that we're working on, folks, these are the different ways that you can solve a system. And for the sake of time, I won't belabor this first page. What's one way to solve a system? Graph. You just graph it, right? I'm not going to do any of this with you. You just know that this is one way to solve a system. You graph. And in fact, I might go ahead and write down here my methods. So one method for solving a system is graphing. And since we all did that graph on the first page, I don't think we need to do another one. What's another method for solving a system? Well, I think I'm done now. I can put my screen back. Yeah. What's another method? I've got here some cute word problems. Could I have one of you read it for us out loud? How about Julie? Since you didn't get to participate last week, please read number 1 out loud for us.
A farmhouse shelters 9 animals. Some are oxen and some are geese. Although there are 22 legs, how many of each animal are there?
Okay, great. So folks, we've got this problem, and we know that there are 9 animals, right? And you might be saying, what kind of crazy problem is this? But it's a great problem. Some are oxen, so some number of oxen, oxen, and some number of geese. So it could be like 1 ox and 8 geese. It could be 2 ox and 7 geese. It could be 5 ox and 4 geese. We don't know. We don't know what combination it is. But what we do know is that there are 22 legs. Now, again, this might sound silly, but there are 22 legs. How many legs does an ox have?
4.
4. And how many legs does a geese have?
2.
The goose, 2. So we need some combination of ox and geese with those leg amounts to produce 9 animals with a total of 22 legs. So how do we solve this problem? Well, one possibility is just random guessing, right? What if we just randomly guessed? And that's what I'm going to do here. I'm going to randomly guess that we know that for every, let me make a little table here, for every ox, you've got 4 legs. And then for every goose, you've got 2 legs. And why don't we try just going ahead and plugging in 2 numbers that add up to 9? So pick 2 numbers that add up to 9. Shemaya? 5 and 4. Let's just try it out. 5 ox, 4 goose. So 4 times 5 is 20. 2 times 4 is 8. That's 20 plus 8. That's 28. Is that the correct number? Oops. Is that the correct number of legs?
No.
No. Okay. Now, right now, that method that I just tried is called guessing. Okay? You could just try to guess. But guessing, nobody wants to guess. Nobody's going to pay you to guess. That takes too long. So another method you could do, and this one is great, it's called systematic guessing. or systematic listing. You can just say, well, hey, there's only 9 animals. This won't take too long. I'll go ahead and just try them all. I'll say I could have 0 ox and 9 geese. I could have 1 and 8, 2 and 7, 3 and 6, 4 and 5, 5 and 4, 6 and 3, 7 and 2, 8 and 1, 9 and 0, right? That's it. Those are the only possible combinations of ox and geese. I'll just try them all. And so then you go through, and again, you know that you're multiplying the first number times 4 and the second number times 2, because that's, you've got 4 legs on an ox and 2 legs on a geese. And you just start going for it. So let's see, that'd be 0 plus 18, that's 18. And then 4 plus 16 is 20. And then 4 times 2 is 8, plus 2 times 7 is 14, 8 plus 14 is 22. Oh, ding, ding, ding. Look at that, we just found that there are 22 legs. You know, and I could keep on going here. 4 times 3 is 12, 2 times 6 is 12, ooh, that's 24. Anyway, I don't have to keep guessing right now because I already found the right combination. So how many ox are there?
2.
2. And how many geese?
7.
7. And if I were to think of this like a coordinate system, I would call this the x, that the y, and my coordinate would be 2, 7. And I could, you know, I could turn this whole word problem into a system of equations, and guess where the 2 lines would intersect? They would intersect at 2, 7, because that happens to be the pair of numbers that gave me the correct choice for the geese and the ox. I didn't turn it all into a system of equations because I was trying to point out that to solve this particular system, you could just guess at random and say you get the right answer, or you could try systematic listing. Again, neither of those are good options because it just takes way too long to guess or systematically list. This is why mathematicians created mathematics, because guess how people used to solve math problems when you were a cave person? Guessing, right? Like until you finally hit the answer. So that's another possibility for how you solve a system. Let's do another method. Substitution. Substitution is a great method. I bet you're all familiar with substitution. We're just going to do one of these problems to remind ourselves of the method called substitution. And unfortunately, the 2 problems, if you're looking at number 7 and 8, you can just cross those out. For number 7, let's write down number 7. Everyone write this down with me. Y equals 6x minus 11 and negative 2x minus 3y equals negative 7. We're about to try to solve the system by substitution. So what do we do? Now, first of all, what do these 2 equations represent? 2 different lines, right? So somewhere floating in space, you've got 2 different lines. They're intersecting somewhere, presumably, and we would like to find that coordinate x, y of wherever they intersect, right? So how do we go about solving this by substitution?
Move the 6x over.
That's if you're going to use elimination.
Oh.
Yeah, and that's what we're about to do that in a second.
Oh.
But substitution.
Y equals 6x minus 1 into the second equation. So
Yeah. We're going to substitute one equation into the other equation. And in order to do substitution, you need to solve for one variable, which already they gave it to us. They said, okay, y is equal to 6x minus 11. So in the other equation, I'm going to look at the y variable and replace it with 6x minus 11. So everyone, please do this with me. What you're going to do is rewrite the second equation as negative 2x minus 3 open parenthesis equals negative 7. I call this writing it empty. Why did I leave that big open space where y used to be?
You're plugging 6x.
Yeah, because I'm going to plug in the 6x minus 11. So you plug in the 6x minus 11, and this is why this method is called substitution. You're substituting one equation into the other equation. What do we do from here? Yeah, we'll just go ahead and do traditional algebraic methods, and we distribute the negative 3, so that's negative 2x minus 18x plus negative 3 equals negative 7. What do we do next?
Combine like terms.
Yeah, combine like terms. So we have negative 20x plus 33
Move the
equals negative 7.
Move the 33 over.
Move the 3 to 3 over to the right-hand side. That gives us negative 20x equals negative 40. And then we divide by negative 20. Now this tells us that x is equal to 2. Is that the end of the problem?
No.
No, because in fact, how many pieces of information are we looking for?
2.
2. We need an x and a y. And so far, we've solved for x. But we still need to solve for y because we're looking for a point of intersection. So now that I know x, how do I solve for y?
Put it back in.
Yeah, you plug it back into the first equation because the first equation is already conveniently solved for y. It's sitting there ready to tell you what y is equal to. So now we go ahead and we plug 6 times something minus 11, and we plug our 2 into that. So now we have 6 times 2 is 12 minus 11, which is 1. And now I know that y is equal to 1, x is equal to 2, and our point of intersection is?
2, 1.
2, 1. Okay, so this methodology is called substitution. We're only going to do one of those. Like I said, this is a whirlwind tour of all the different ways that you can solve a system that you've done in the past. These are methods you've done at some point in your past. So that's substitution. Does anybody like substitution?
Yeah.
Yeah, it's a nice method. It totally works. All you got to do is solve one equation for one variable, substitute, and whammo, you're on your way solving. So that's substitution. There's one more method that Julie was alluding to a moment ago, and that's called elimination. Elimination is a fifth method. For solving systems. So let's see here. I think I'm done with my little overview over here. I'm going to go ahead and keep solving over here just in case you're still looking at substitution. So now, did everyone turn the page?
Yes.
Okay. So now we're looking at elimination. So solve by elimination. I'm going to do number 17 with you. So number 17 says 9x minus 6y equals negative 15. And 9x plus 6y equals negative 3. How do we do the elimination method, Julie?
Cancel out this negative 6y and the positive 6y.
Yeah, and how do you cancel them out?
One's negative and one's positive.
Yeah, so definitely the y variable we're about to eliminate because one of them is a negative 6y and one of them is a positive 6y. And how do you eliminate them? Yeah, you just multiply, you just add these two equations together, right? Term by term by term. So the x's have to be stacked, the y's have to be stacked, the numbers have to be stacked, the equation signs have to be stacked. And so we add them all together. 9x and 9x is 18x. The x or the y's cancel out, and then we have negative 18 over here. Right? A lot of people love elimination. For this reason right there, you so quickly get to something simple. It's delightful. So now what do? We just divide off the 18. Oops, just 18. And now we have x equals negative 1. Now again, is that already the answer? Are we done?
No.
No, because how many pieces of information are we looking for?
2.
2. We're looking for x and y. So we still have to solve for y. So how do we solve for y?
Plug it back into the first equation.
Yeah, you just have to plug it into one of those equations. See, notice how solving for x was wildly convenient? Like, whammo, you already solved for x? Solving for y is wildly inconvenient. Because now you got to choose one of those two equations to solve for y. Which equation do you want to choose, Julie?
I chose the top one.
The top one?
Mm-hmm.
Okay, so I'm going to go ahead and write down 9x minus 6y equals negative 15. I'm going to plug in negative 1 for x, so that's 9 parenthesis negative 6y equals negative 15. I plug in my negative 1 for x, and so that gives me negative 9 minus 6y equals negative 15. And from here, this is all just, plug and chug algebra, where you move your 9 over, and that gives me negative 6y equals negative 6. I divide off my negative 6, and I get y equals 1. Okay, now I'm done. I've got x equals negative 1 and y equals 1. What is that information together? It's a coordinate in space, and that coordinate is negative 1, 1. What's happening at that coordinate?
Lines intersect.
Lines intersect. Do I know what the lines look like? No, I don't because I didn't graph them. I have no idea what the lines look like. But I know they intersect right there. Isn't that cool? I have no idea what the lines look like. They could be anywhere, but except for the fact that I know that they intersect right there. For all I know, it looks like this. For all I know, it could look like that. But what I know for sure is that the two lines intersect right there. Okay, folks. Like I said, this was not necessarily a like a full lesson per se. This is just a review of previous concepts you've used in the past to solve systems. So I have one more example here. Number 31 and 32. And this is a really nice lead-in to what we do in this class. What we're going to get in this class is lots of word problem scenarios in which we have to solve the system, meaning finding the point of intersection. It will come in the form of a word problem. We have to make the equations ourselves, solve them ourselves, and get the point of intersection ourselves. So the school that Elisa, do you think her name is Elisa? 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 I think it's Elisa. The school she goes to is selling tickets to a play. On the first day of ticket sales, the school sold 12 senior citizen tickets and 3 child tickets for $81. Now just right there, how do we turn that into an equation?
We want to do 12x plus 3y.
Yeah, that's perfectly fine for me. 12x, that is 12 senior citizen tickets, and I don't know how much the tickets cost, so we call it x. 3 child tickets, I don't know how much the child tickets cost, so we call it y. But we know that together, it adds up to a total of $81. So just real quick, what does x represent?
The cost of the tickets for seniors.
Yeah, cost for seniors, right? And what does y represent? Cost for children. Now, who thinks that's fair? Oh, wait, no, we don't know yet, really. Sorry, I almost thought that a child ticket was $3 and a senior ticket was $12. That's not true, right? That's not what this is saying. What does the 12 mean?
12 is number of tickets.
Yeah, 12 senior citizens came and 3 children came. But we don't know how much it costs yet. I just know that together it cost $81. Okay, what's the second equation? The school took in $65 on the second day, so $65 on the second day, by selling 6 senior citizens and 5 children. So 6 senior citizens and 5 children. Okay, well that's all the information, right? What's the price of each senior citizen ticket and 1 child ticket? Now this is our bread and butter right here. A system written in this form right here. Because with this form, we could use any of these methods, right? We could go ahead and convert all those equations to y equals mx plus b, graph them on a graph, and find the visual point of intersection. We could go ahead and just start guessing. Like, well, how much can a senior citizen ticket cost anyway? And just start guessing. We could try systematic listing of trying different costs for adults and children. We could go ahead and do substitution, although to do substitution, you'd have to solve for x equals or y equals, so that might not be very convenient. Or we could do elimination. And maybe elimination would be our best bet. Which of these variables could we easily eliminate? X, right? Because this one's already a positive 12x. Can we turn that into a negative 12x?
Mm-hmm.
Yeah, what would we multiply?
-2.
Yeah, we multiply by -2. Now, I'm going to go ahead and start the problem. So that's negative 12x, and then that's negative 10y, and then that's negative 130. So you can see where we would go with this. We would transform one equation by multiplying the whole thing by -2, and that's called a row operation. Because we're multiplying the entire row by a single number. That's a row operation. So now we can go ahead and add the top equation to the bottom equation. You'll notice that the x's cancel out. 3y minus 10y is negative 7y. And then 81 minus 30, I'm sorry, 81 minus 130, what's that?
49.
What is it?
Negative 49.
Negative 49? Oh, goody. I'm glad it's 49 because that's divisible by 7. So we divide off the negative 7, and we get the y equals 7. So how much, what is that, $7 for a senior or a child?
Child.
Yeah, for a child, because it's the y variable. Okay, so then how would we solve for x?
39.
Yeah, plug it back in. So I am going to go ahead and finish it. So 6x plus 5y equals 65. And instead of y, I'm going to plug in 7. And then that gives me 6x plus 35 equals 65. Getting rid of the 35, we have 6x equals 30. And so x equals 5. Okay, do those two things seem reasonable? That a child costs $5 and a senior, no, I had that backwards. A senior costs $5 and a child costs $7. What? What's that, Shemaya? Oh, you're just sneezing. Okay. All right, well, that's the solution to that particular system using elimination. You could have used any of those methods, but we did elimination because it looked convenient. Now, I'm going to go back 1 second here. Look at the original setup. This original setup. There we go. that original setup for the rest of the evening, what we'll be doing is taking the coefficients and turning them into a matrix. 12, 3, 81, and 6, 5, 65. And that is how we're going to solve problems for the rest of the evening. You take a scenario, some sort of a word problem, you capture it into some sort of equations, you make sure that the equations are in standard form, meaning x variable, y variable, equal sign, number, and then you go ahead and put it into a matrix. And that's where our fun begins, is how do we manipulate a matrix to get a solution for this problem. So, yeah. Okay, so that's our introduction, folks. That's an overview of what we're getting into. So, a whole new way, matrix methods. So we're going to use matrices for the rest of the evening. If I had room right here, I would write down 6 matrices. And that's what we're doing. Now, chapter 2 covers a wide variety of matrix methods. My goal is for us to do all of them tonight. So, now, who remembers why matrix methods were invented? Exactly. It's kind of laziness, right? Because, you're always dealing with x's and y's and equal signs. We don't want to write them down over and over again. So we think, gosh, what if I can just get to the heart of the problem, which are the different coefficients? And what if I can just manipulate the matrix in order to solve the problem? Then I don't have to keep on writing down x, y, equal sign. So it's just a little bit more convenient, believe it or not. So the first method we're going to look at tonight. Okay, so everyone, that was it for your interlude packet. You can now switch over to your chapter 2 packet. So does everyone have chapter 2? Okay, dandy. And we're looking up at the first one? Okay. Now, what I have up here on my board is I have the echelon written down. And let's go ahead and look at the definition. And then we'll may or may not look at an example. And then we'll do number 1 together. Yeah, there we go, number 1. So first, let's just go ahead and look. This is section 2.1. It's called the echelon method. Have you ever seen this word before, echelon? Maybe, maybe not. What does echelon mean? Anybody know? I believe. Is it what?
Like a line.
Well, kind of, Nick. I think that's, that's along the lines there. Now let me see here. Where are all my windows? This computer is so weird.
Press the Windows button. It just kind of freezes. I'm sorry, on your keyboard.
Oh,
And then give it a minute, and then everything will come back up.
really?
Just hold, please.
Oh, there it is. Okay. So if I go ahead and go to a web page here, and I type in echelon. Well, jeez. Oh, I know. I'll look at images. No.
If you, talk about like aircraft, if you give it like
Echelon formation?
like in a echelon left or right, it's a straight line pretty much.
Oh, I see what you're
Slant to the
saying.
left or right.
Yeah, okay, yeah, and in airplanes, so if you look up at airplanes up in the sky, oh, fun. So these are various echelons, I suppose, various formations, or because Nick was talking about airplanes, here you go. You've got different airplanes, echelon right, echelon left. Ultimately, and that is actually what we're talking about. It's putting things in order, just like these guys are. Echelon left, echelon right. Thank you, Nick, for mentioning that. That's what it means. It's a diagonal. An echelon is a diagonal. You could also refer to it as part of a triangle because you're kind of making a triangular shape. So now that we all see what echelon is, although that didn't really give us the definition, did it? Definition. Echelon, no. Oh, look at that. A body of troops arranged in a line, a diffraction gradient, no. Okay, well, yeah, so it's the troops arranged in a line. There we go, echelon. What we're going to see, now that you hear that definition, look at these systems and what about it looks like echelon. The word echelon. Especially this one, it's pretty suggestive. Do you see how the x, y, z variables are in that echelon form? They're in that nice diagonal line. That's echelon form. That's what we want to do. We want our system to look like this. And likewise here, this is a smaller system of only 2 variables, but you see that the x and y variable are still in the echelon form. It's a diagonal. What's nice about it is you'll notice the bottom equation is very easy, right? It's already solved. Z is equal to F. And once I know Z, once I know that Z is equal to F, what can I do with the F? I plug it into the equation right above it, and then I'd be able to solve for Y. And then once I know Y, I can take Y and Z, plug it into the top equation, and solve for X. So it's this really interesting method where you're given a full system, and you make your system, you manipulate it so that the bottom row goes 0, 0, and then Z. The next row goes 0, and then Y, and then there. And then the top one has all those numbers. So ideally, right here, if I wanted to take this system and put it in echelon form, my goal would be that after I'm done manipulating it, I would get it to be something that looks like 0, 1, 7, and then 1, 8, and 6. There. This would be an echelon form. And it's an echelon form because I've got this diagonals of 1 right here. And that looks like an echelon. Because now I know that this column represents my x variable, this column represents my y variable, and looking at this, I already know what y is equal to. What is y equal to? 7. Because if I go back and put in all my variables, this is really y equals 7, that's x plus 8y equals 6. Do you see the original equations? So now I clearly know that y is equal to 7, and I take it and I back substitute it into the top equation, and I'd be able to solve for x. Okay, so that's conceptually what we're about to do, is take a matrix, like this matrix, and turn it into echelon form. Now the question is just, how do we turn it into echelon form? So they give us an example. I don't think we'll look at this, because if you just look at this, that might overwhelm you. It's pretty long. Let's just do one together, shall we? So let's go ahead and do this first one together. So we're going to do number 1. I keep misplacing on myself. Okay. Now, folks, this matrix methods, maybe you did it before in your past, maybe you didn't. So I'm just going to pretend that we're all new to this together. Let's go ahead and first take your equations there, and let's write down the matrix. What matrix are we going to write down?
1, 6.
Yeah, 1, 6, 13.
-3, 5.
-3, 5. And -16. Okay. Everyone feel good there? We wrote down the matrix. We still know what everything represents. We still know that this first column represents x. We still know that this column represents y. We still know that this column represents a number. We still know there's an invisible equal sign right there. But we don't bother writing all of that because we're fundamentally lazy. Okay. Now, my goal, I'm going to write down my goal statement here. By the time we're done, I would like this matrix to be 1, and then a number, and then 0 and a 1, and then a number. That's my goal. Our goal is to manipulate it so that we have this echelon row. So, how are we going to do this? This is a lot of numerical computation. So, my first thing I'd like to do I already have a 1 there?
Mm-hmm.
Yeah, great. So, you always go vertically down. You take care of the first column at a time. This is the one I want that to be a 0. So, to make this a 0, I'm going to have to take the entire first equation. And how do I cancel out a -3? With a
-3.
with a +3. So I'm going to take this whole top equation and multiply it by 3. Because now this is going to be 3 times 1 is 3, and 3 times 6 is 18, and 3 times 13 is 39. And now what I'm going to do is take those numbers that I just got and add them to that row. So, and that will give me my new matrix. Now I'm going to use different colors. I don't know how you're going to make this more clear on your own paper. If you have different colors, that could be helpful. Or if you just write really small to make it obvious that you've got your regular numbers and then your computed numbers. But you want to somehow distinguish. So now I keep my first row, because nothing happened in my first row. I'm actually going to keep it. I'm not actually changing it. I just had to do a computation to know what it would be if I did multiply it by something. Now I'm going to go ahead and add my computed numbers to the bottom row to create a new bottom row. So 3 plus -3 is 0. 18 plus 5 is 23. And 39 minus 16 is what? 23. Now what we just did right there is bread and butter for the whole rest of the class and for the next class as well. How are we doing with our goal so far? We're doing pretty great. We've already got a 1 and a 0 in the first column. Now we need to move on to the next column, where what's our goal?
13 and negative 16, are you adding them? Well, no, man.
I'm always adding them together. 3 plus negative 3 is 0. 18 plus 5 is 23. 39 plus a negative 16. And we're always adding. But I mean, in this case, you're also just doing 39 minus 16. Okay, so the next goal is to have a 1 at the bottom. We don't have a goal about this number. It's just some number. But we definitely want that one to be a 1. So now, how do I make this number into a 1? Fundamentally, all we can really do is multiply the whole equation or divide the whole equation. What can I divide this whole equation by to make that a 1?
23.
23, right? I'm going to take this whole thing and I'm going to divide it by 23. And so that would give me, obviously, a 1 and a 1. And actually, that is going to become our new matrix. So now I have still the 1, 6, and 13. And I'm going to take this equation and replace it with that same row, but dividing everything by 23. Now you'll notice that what we just did was different from the first thing we did. In the first one, we multiplied the other row and then added it to itself. In this one, we just straight up divided the whole row by something. Okay, how are we doing with our goal?
Good.
Yeah, we're there. We're already there. We are now in echelon form. We are now in echelon form. We did it. We did it only doing 2 row operations. And now how do we interpret these results? How do we interpret what just happened? You might find it helpful to go back and think about the fact that that's an X and a Y and an X and a Y, and those are equal signs right there. Because it's in echelon form, we now know what the bottommost variable is. What's Y equal to? 1. So now I know that Y equals 1. And now the key is we're going to back substitute. Once you make this echelon form, you go all the way to the bottom, and then you start working your way back up again. So now we're going to plug 1 in for this Y. So we kind of have to go somewhere and do some work for that. This equation is 1x plus 6y equals 13. And where the y is, I'm going to put a 1. So 1x plus 6 times 1 equals 13. And so that gives us x plus 6 equals 13. And therefore, x equals 7.
And we would still put a final answer as a coordinate, set of coordinates?
Correct. The final answer is always a coordinate. Because here's the thing. This is 2 equations. It's 2 lines on a graph. We have no idea where, well, now we know where they intersect. We don't know what the lines look like, do we? We don't actually know where they are, what their slope is, or what angle they're at, but we know that they intersect at the point 7, 1. Yeah?
And it always has to get to the 1, 1.
Yep, your echelon form is a diagonal of 1s.
Will you ever do multiple, subtraction with it as well?
Yeah. In fact, we're going to do a lot of different. I mean, fundamentally, what you can do is you can multiply an entire row by a number. You can divide an entire row by a number. And then you can add 1 row to another row. That's fundamentally what you're allowed to do. You can multiply a whole row by a number, divide a whole row by a number, or you can add 1 row to another row and replace it.
So since, wouldn't essentially our 2 equations be x plus 6y equals 13 and y equals 1? So we can technically plot one of them, right? Like the y equals 1 line.
Oh, sure.
And then,
Yeah, and just to say what Lauren is doing, one of the equations is x plus 6y equals 13, and the other equation is y equals 1. Absolutely. And if you wanted to graph that, we know what this one is. Everybody, what's the equation y equals 1? What kind of line is it? Horizontal. So we know we have a horizontal line at y equals 1. And now this one, x plus 6y equals 13, you'd have to solve that for y and solve for y equals mx plus b.
But since we know they cross at 7, 1, we know that that's where the other point.
Right.
That's where their intersection. We just don't know how the other one looks.
Yeah, we just don't know what the other one looks like. Yeah?
Quick question. Yeah, like I found this a bit more difficult. Can we use this as elimination?
Oh, what a great question, guys. Maybe you're already more comfortable and familiar with elimination, substitution, and graphing, and you love those methods, and you're like, bam, bam, boom, I'm just gonna do the other method. No. Yeah, no.
Not for this chapter.
Yeah, for this chapter, this is just the baby skill right now. What we just did with echelon form is the simplest form out of the ones in this chapter. We're building on this, and we're gonna learn even more matrix methods. In order to take the test on chapter 2, you will have to demonstrate for me matrix methods. So Anna, you could do it this other way, and you would just get no credit on the test.
Okay.
All right. But you could do it that way to check your work.
It?
Absolutely, you can check your work that way. Yeah. But right now, we should all just submit ourselves to the process, and our goal is to learn how to do the process. Now, just for fun, this equation, if you did go ahead and solve it, it'd be y equals -1/6 x plus 13. No, 13/6. And so that would be a y-intercept of right around here, and then a slope that would look like this, and that's what it looks like. So indeed, the two lines do cross at 7,1. Okay, let's keep our momentum going. Now, notice.
Quick question.
Yes, Carmen.
So why is there times 3 on the base?
Why did we do that one? Because I wanted to turn that number into a 0. Now notice, I can't turn a -3 into a 0 with multiplication or division. The best I could do with multiplication or division is turn that into a 1, if I divided the whole row by -3. So I had to somehow add this equation to this equation, which is elimination. To Anna's point, that is elimination. So I had to multiply this equation by 3 to get a +3 and a -3 so that they would cancel out and turn this number into a 0.
But why I cannot just divide by -3 on the whole row?
Ah, everybody, thank you, Carmen, for that question. What if I had just divided this whole row by -3? Watch what would happen. -3 divided by -3, 5 divided by -3, 16 divided by -3. That would have been a 1. That would have been a -1.6 repeating. And that would have been a 5.3 repeating. What would have happened? Ugly city. That'd be unfortunate. Yeah, things get crazy, and then, yeah, no, we don't want all those decimals. And plus, that's not even a 0 yet. So how would you turn that into a 0? You would have to first multiply this whole thing by negative, so it'd be a negative and a positive and a negative, and then add that row to this row, because then that would get rid of that -1 and turn it into a 0. Carmen, did I answer your question?
I know.
Okay, I think the best thing that we could do right now is try another example, because we need to get more comfortable with row operations and how they work. So, folks, I desperately want to answer your questions. I'm so glad that 3 of you just now asked the question, and I want more questions, but we should really do another example, because I think another example would clarify more. So let's try this next one. What's our matrix?
6, -6, 7, and -10.
Yeah, and then?
-4, 5, and -6.
Yeah. Okay, and in this case, yeah, we're a long way from our goal, aren't we? I shouldn't have erased my goal. Our goal is 1, 0, a number and a 1, and then some numbers. That's our goal, so that we have that. Okay, now, yeah.
Will that be always our goal? We want.
In echelon form.
Okay.
Yeah, this is section 2.1, echelon form.
Okay.
Yeah. Okay, so how do we cancel one of these?
Can we first change the top one to a 1? That way we don't have to deal with big numbers?
We could.
No.
But to turn this to a 1, we divide everything by -6, and then you'd have a bunch of nasty fractions, right?
Can we just multiply both of them by like -2 for those who could be 4?
Well, we certainly could do that. We could go ahead and make them the same number, first of all.
But
Just
their
to,
lowest common is 12.
Yeah, 12.
yeah, so we could multiply. Let's go ahead and try it. Let's multiply the top equation by what, 2?
Yes.
And the bottom equation by -3? Because we need one of them to be positive and one of them to be positive. One of them negative, one of them positive. So now I'm going to go ahead and just replace the whole matrix. So we'd have -12, 14, -20, and then 12 and -15 and 18. Yeah. Now here's the thing. I think what we've all noticed already is that if we had just tried to turn this into a 1, we would have ended up with fractions. So really what we're going to try to do is just turn this thing into a 0 first, and then we can go ahead and divide through and make everything fractions, because that's the last thing we'll do. So our row operation that we're about to do is to go ahead and add, we're going to add this equation onto the bottom equation and replace the bottom one. Okay? We can only replace one or the other. So I'm going to take the top equation, add it into the second equation, and replace what I get. So to make that more clear, go ahead and just copy the first equation, or the first row again. Negative 12, 14, negative 20. Just keep it. Because we can only add one equation at a time. So now add those numbers together. Negative 12 plus 12 is 0. So we're making a new second row. 14 minus 15?
Negative 1.
Negative 1. And then negative 20 plus 18?
Negative 38.
Okay.
Sorry.
Hey, this is actually looking pretty good,
Oh.
right? Now, we're really close on our goal on the second row. We want that to be a 1. So what are we going to do? Yeah, we're just going to multiply the whole bottom equation by negative 1. If you wanted to show all of your work, you would do some sort of indication that you're multiplying by negative 1, and then you rewrite the whole matrix. Now, that's kind of what matrices are all about. You end up rewriting and rewriting and rewriting and rewriting, so you get used to it. So we've reached our goal for the bottom row. We have 0, 1, and then a number. And all we need now for the top row is divide everything through by negative 12, and that will give us our top row goal. So I'm going to divide negative 12 on the top, and I'll go ahead and show my work. Divide by negative 12, divide by negative 12, divide by negative 12. And now my new matrix is going to be 1, negative 7/6, and positive 5/3.
Yes.
All right, there we go. Now, first of all, folks, this is really exciting. This is super fun. This is absolutely what we wanted to do. Have we achieved our goal?
Yes.
Yes, absolutely. It's an echelon form. We've got our echelon of 1s. We've got that 0 down there. And do we already know what y is equal to?
Yes.
Yeah, y is equal to 2. So now I know that y is equal to 2. And I remember this is my 1x, this is my 7y, that's equal. How do I find out what x equals?
Because the y equals goes over to the right, right?
Well, yeah, I'm no longer a matrix. Yeah, so now I know that y equals 2. I'm going to come up here then. I now know that y equals 2. And the purpose of echelon form is once you're in echelon form, you automatically know the bottom variable, and now you back substitute. That's the key phrase, back substitution. That's the phrase they use in the book, back substitution. You do back substitution to work your way back up to solve for x. Now, at this point, when you do back substitution, you're no longer dealing with matrices. You don't keep dealing with matrices. We did matrices just to manipulate this into echelon form. Now you're just doing standard algebra. So I write down 1x minus 7/6y equals 5/3. And so what am I plugging in for y? 2. So now I have x minus 14 over 6, or I can cross cancel. And so that's 7/3. X minus 7/3 equals 5/3. Guess what really satisfying thing is about to happen? All the fractions are going to go away. Because I move the 7/3 over, and I get x equals 12/3, which is 4. So we go back into the realm of whole numbers. And what's our actual solution?
4x.
Yeah, the coordinate 4, 2. Now, the coordinate 4, 2. We don't know what the lines look like. They could be up, down, right, left, who knows? But I know that they intersect right there at the coordinate 4, 2. What's that, Anna? Yes, now Anna. Anna has a really great point, folks. Was that a lot of work?
Mm-hmm.
Yeah. I mean, computationally, we're going to be doing a lot of computations. And again, for today, you just get used to it. But what's the worst? You multiply a whole row by a number, you divide a whole row by a number, and you add 2 rows together. So, I mean, it's basic computation. There's just a lot of it. Now, the irony, you might be sitting here asking yourself, Mr. G, I thought you said they invited matrices because they were lazy. This doesn't seem like the work for lazy people. This seems like a lot of work. But guess who can do this work so easily? A calculator and an Excel spreadsheet. So did they design these methods for a human to do? No. They designed these methods for a calculator and a computer to do. Because you know what calculators and computers can't do? They can't actually graph things. You know, they have graphical displays and they show you what a graph looks like. But every time you ask a computer or a calculator to solve a system, do you know what they're really doing? They're really doing this. So right now, today in this class, we're learning the language of computers so that we can understand what a computer is actually doing when it solves a system. All right? It's really quite exciting. Now these row operations, we'll keep on practicing them to get better at that. Number 3 I left as a homework problem, but let's go ahead now and try number 4. Number 4 is very exciting. You're all going to be on the edge of your seat for this one.
No, I don't like that.
What's the matrix?
5, -2, 1, 2,
Yeah, 5, -2, 2.
and 25, -10, and 6.
25, -10, and 6. All right. Now remember, even though our goal is to have a row of 1s, we'll wait to the end to actually divide everything through to make it a 1. So what's our real goal first?
0.
Yeah, we want to make that a 0. That's our real first goal.
So just multiply the top number by -5, correct?
Yep. Folks, we're going to multiply the entire top equation by -5, because that way that'll turn it into a -25, a +10, and a -10. And then we add those numbers into the second row, right? Because the first, you can actually leave the first row untouched. You can leave it as 5, -2, 2. You know, you're not really multiplying it if you don't want to. You're just thinking about what those numbers would be if you did multiply it, and then adding those numbers into the second row. So what happens when you add them into the second row?
0, 0.
0, 0, -4. Now, are we all feeling lucky? We're like, hey, sweet, there's even more zeros. This is great.
No.
Wait a minute.
Yeah, because what does this equation represent? 0x plus 0y equals -4? Can 0 equal -4?
No.
No, that's impossible. 0 does not equal -4. So we stop for a moment and we ask ourselves, 0 doesn't equal -4. This is false.
Mr. G.
Yeah.
Is that 0, 0? I'm confused. Are we, when we were doing that, weren't we substituting in for the first row?
Oh, I wasn't substituting for the first row. I was just thinking about what the first row would be if I multiplied in those numbers.
Okay.
And then I added that row on top of the second row.
So that would take place of the second.
So yeah, we were
Okay.
replacing the second row.
Gotcha.
Okay. So now, folks, what does that mean anyway? That we apparently have a false statement coming out of this thing. Let's remember what the question was. The question always is, how do you solve a systems of equations? What are you looking for? A point of intersection. So what's the question we're always asking? Where do they intersect? Is that the question?
Yes.
That's the question. So the question is, where do they intersect? What answer did we get?
No.
False. So what does that mean about where they intersect?
They don't.
They don't. These two lines don't intersect. So this is a parallel system. They are parallel. They don't intersect. So what's the answer to number 4? Parallel. You'd say parallel, no solution. Yep, parallel, no solution. Now isn't that interesting? Isn't that interesting? This math, you really can interpret it. You can interpret it like a conversation with a friend over IM. Okay, maybe not like that. Now, folks, since we're all still kind of starting out these row echelon business, should we do number 3 together?
Sure.
I feel like maybe we should. Because I don't want to. I would rather us really understand these methods as we go and not get to some of the material at the end. But I really want everybody to be on board as we move forward. Because Lorena just asked a great question. She said, hey, wait a minute, we didn't just write down a new row? I thought we were changing the first row. So we need to be very clear about our intentions and how we're manipulating these things. So can I show, well, I'm going to keep my goal. I would like to go back to Lorena's question.
Will we always be replacing row 2?
Well, our goal is to get a 0 right there.
Oh, okay.
So yeah, kind of.
Right,
Yeah, that is what we'll be doing. We'll be replacing row 2. Now everybody, take a look at what I could have done for Lorena right here. I could have multiplied the whole top row by -5 and gone ahead and replaced it. It could have been -25 10, negative 10, and then I'd have the row 25, negative 10, and 6. But I know maybe that's what you're expecting me to do.
Yeah.
And now I would still go ahead and add them together and replace that row. So now I would go ahead and I would keep the negative 5, 10, negative 10. Now add them together to create a new second row, which would be 0, 0, negative 4. And then what would I have to do, Lorena? Go back to this one, and I'm just going to have to divide that out anyway.
Gotcha.
So that's why I just did it imaginarily. Because I'm just going to take that negative 5 out anyway later. Okay, did that work?
Yes, that's where that's how I was setting it up before.
Okay, and that's perfectly fine if you want to do that way. It's just a computation you didn't need to keep. Okay, so let's try another one, folks. Number 3. What's our matrix?
5, 24.
Yeah, 8, negative 5, 24. And then negative 4,
Negative 3,
3.
negative 12.
Great. That pen is now trash. That's not trash.
Can you
Okay.
can you multiply the bottom row, or do you have to do the top row?
You can multiply the bottom row. That's just fine. Great question. There's a lot you can do. You're free to manipulate it however you like. The basic rules are you can multiply a whole row, you can divide a whole row, and you can add one equation into the other and replace a row. Okay? So those are your options. You can either multiply the whole row, you can divide the whole row, or you can add them together to replace one of them. Add together to replace. Meaning, every time you add the two together, one of them you keep, one of them you replace. So let's try it. What do we want to do? You just had an idea, Julie. You want to multiply the whole bottom one?
Yeah.
Let's do it, guys. Let's multiply the whole bottom by what, Julie?
2.
2, right. Because now we have a whole new matrix, which is 8, negative 5, 24, and then negative 8, negative 6, and negative 24. So that was one option. All I did was just multiply a whole row by a number. That's one option. Now you can add 2 rows together to replace one of them. So one of them stays the same, and the other one changes. So, Julie, which one do you want to keep?
Top row.
So keep the top one. But now we're going to replace the bottom row with the sum of both rows together. This is the other legit move. So Anna, if I add both of them together, what do I get?
0,
0.
negative 11, and 0.
Right. That's it. So you keep one, replace the other by adding the 2 equations together. You can subtract them together too, but I mean, addition and subtraction are essentially the same thing. All right. So folks, we did it. We have the 0 here. That's all that really matters, because now how do I turn this into a 1? Divide the whole equation by negative 11. Right? That's actually pretty easy because the rest of them are zeros. So if I divide that by negative 11, that gives me 0, 1, 0. Now what about the top equation? What am I going to divide everything by? Because what do I want this number to be?
0, 1.
I want it to be a 1, so I divide everything by 8. So I'm going to divide everything by 8, so that by 8, that by 8, that by 8. And that gives me 1, oops, wrong color. That gives me 1, negative 5/8, and 3. Now, did I do it? Did we achieve our goal of echelon form?
Yes.
Yeah. Through a variety of manipulations, we achieved echelon form, and now you can kind of pretend to put the variables back. You know that 1y equals 0. Well, that's easy. Y is 0. And then you have 1x minus 5/8 y equals 3. And so now we start back substituting. So I know for sure that y is equal to 0. And now in my second equation, I have x minus 5/8 y. Whoa. X minus 5/8 y equals 3. And so for the y, I put in 0. But 5/8 times 0 is just 0. So now I have x equals 3. And so what's our point of intersection?
3 and 0.
3, 0. Again, I have no idea what the graph looks like, but I know that my 2 lines intersect at 3, 0. It could look like this or this. I have no idea. But I know that the lines intersect at 3, 0. Did that feel a little better? Now listen, it's so important that you guys are raising your hands and asking your questions, because we're just doing more and more of this for the rest of the night. So if the row operations are feeling strange, let's ask questions. So what can we do? You can multiply a whole row, you can divide a whole row, or you can add 2 rows together, replacing one of the rows with the sum and keeping the other row just as it is.
Does it matter which one we replace?
Not at all. You could add them and replace the top one, add them and replace the bottom one. Julie.
And you don't have to rewrite the row. You can just do the division in like both rows, like you did in the third box. Yeah.
Yeah, you can divide both of them and then write down your final answers.
But I mean, you don't have to rewrite it again. You just do it again in the same box.
Oh, well, now see, that all depends on how neat and messy your work is going to be. I think that you should go ahead and rewrite it. Wait, are you talking about how we replaced, like here, I did it right there in the same box as a temporary placeholder for the work I was doing? Or are you saying?
Here you actually.
No, how you did each row in the same.
How you do them both at the same time?
There
Oh,
you go.
yeah, you're allowed to
thank
do
you.
them both at the same
Not just
time.
one
Yeah.
row at a time. Then
Oh,
one
yeah,
time.
you can do them two at the same time, yeah. Yep, that's fine. But you still got to write your final answer, right? Okay. Great, folks. Oh, boy. Matrix methods. Talk about exciting. Who really likes matrix methods? What really likes matrix methods?
Calculators.
Calculators and computers. That's why we're learning it, because it's the language of calculators and computers. Okay, moving along. Number 5. Ooh, what is different about number 5?
There's a lot more numbers.
A third variable. Still only 2 equations, right? Yeah, now, what is the matrix for number 5?
7, 2, -3, and -3.
Mm-hmm. And?
-3, 1, -4, and 2.
Yeah, 2. Great. What is echelon form for this? What's our goal statement?
Isn't it 0?
1, 0. See?
Our goal still is just focused on the beginning. The echelon form always has to happen at the beginning. So we're still looking to get a diagonal of 1s with a 0 in the bottom. The only thing that's going to be weird about this is the fact that we have 3 variables. So when we solve, so everyone take a look here. We know that this is x, y, and z. I'm going to be able to solve for y, but it's going to be in terms of z. I'm actually going to have a y equation that has a z in it. And I'm going to say, okay, well, that's my formula for y. Y is equal to something z plus a number. And then when I back substitute, I'll be able to get a formula for x in terms of z as well. So I'm going to have, in the end, I'm going to have something like, I'm going to have something like y equals 2z plus 3, and then I'll have something like x equals 3z minus 8. And it's going to give me the formula for x and y in terms of our dummy variable z. So it's kind of like, once you choose what the z value is going to be, then you can say what x and y are. So I can say, let z equal 5. And then I would have a particular solution for x and y. I can say, let's let z equal -10. And then I would have a particular solution for x and y. Julie?
Is z the same number or is z?
Yep, z is the same number in both cases. So let's just say that I said, let's let z equal something easy, 1. All right, so we're just saying, okay, z is equal to 1. Z might be the number of, I don't know.
So on the echelon form, it'll be 1 up there.
Yeah, there'll be a 1 and a 0 and a 1, and then those will just be any old numbers.
Okay.
Yeah, but let's just say that I did finish and I got this out. Then provided that z is equal to 1, then y would be equal to 2 plus 3 is 5, and x would be equal to 3 minus 8 is -5. And we would say that that is one particular solution for that system of equations, depending on what number you chose for z.
And you need to include z in the final.
Yeah, z is going to be in the formula for x and y.
But not in the matrix.
Yeah.
Because C can change.
Yeah, z is going to be whatever. The echelon form doesn't reach z, so those are just going to be numbers. Let's go ahead and do one, and we'll see how it works out. So here's our matrix. Again, the first thing we really always want to do is turn this into a 0. So let's go ahead and turn that into a 0. How are we going to do that?
Multiply by 7.
Yeah, bummer, right? We'll have to multiply the top one by 3 and the bottom one by 7. So we might as well go ahead and multiply all the way across there. So now my new matrix is going to be 21, 6, -9, -9. And then -21, 7, -28, 14. Did I get that right?
Mm-hmm.
Now, folks, again, are these a lot of steps or not a lot of steps? It's a lot of steps. Are the computations hard or easy? The computations are easy. It's a lot of steps. It's a trade-off. That's always what it is in mathematics. It's a trade-off. You can have lots and lots of steps with simple calculations or 2 steps with hard calculations. Okay, so now what are we going to do? Whenever you add 2 rows together, you keep one and you replace the other. So let's keep the top one, 21, 6, -9, -9, and replace the bottom one. And what will we replace it with?
0.
0.
13.
13. -37.
5.
And 5. Way to go. Now the only thing left for us to do is divide the whole first row by 21 and divide the whole second row by 13, because that will turn those first 2 numbers into a 1. So we go ahead, we divide the whole first row by 21, and I'm going to write little fractions here just to help me visualize what my fractions are going to look like. And then I divide the whole bottom row by 13. I'm going to draw my little divide by 13s to help me see what they look like. And then I'm going to write down my final form. Now, folks, this is not going to look pretty. 6/21, which simplifies to 2 7s. Yeah, 2 7s. And then -3 7s. And then, -3 7s as well. Okay? And then the next one would be 0, 1, -37 13ths, and 5 13ths. It does not look pretty at all. And you know what? A lot of times math doesn't turn out to be pretty. But do you know who does think this looks pretty? A calculator and a computer. They have no problem with this at all. So now we remember all of our variables. That was really x, y, z. This is really y, z. And we go ahead and write down our equations. So this equation is y minus 37 13ths z equals 5 13ths, right? But what I really want is a formula for y. So how do I get y by itself?
You add the.
Yeah, I just add the 37 13ths z to the other side. So really my formula for y, I'm going to write that one down here. Well, I'll keep going right here. Y is equal to 37 13ths z plus 5 13ths. Okay? So that's what y is equal to. As soon as you tell me what z is, your choice, you just choose a value for z, I can tell you what y would equal in that scenario. Okay, now how do we solve for x? I say x plus 2 7ths y minus 3 7ths z equals -3 7ths. I really want the formula x equals, so what do?
Move everything over.
I move everything over. That's it. You just move everything over, which ultimately means you change the sign on those 2 numbers and put them on the other side, right? So now I have x equals -2 7. Oh no, there's actually something we didn't do yet.
So you don't plug in.
Yeah, I'm sorry. We're supposed to back substitute. We have to get rid of y.
So we do plug in.
Yeah, we plug that in
okay.
to back substitute. Now right there, your brain might just drop right through to your chest and you might want to cry. Right? Because technically to present our final answer, it has to be x in terms of z and y in terms of z. So let's just see how terrible this is. X equals -2 7ths times y, which we now know what y is. It's 37 13ths z plus 5 13ths. Continuing on our merry way, -3 7ths z minus 3 7ths. Now we haven't distributed yet, but do we in fact have a formula for x in terms of z?
Yes.
Yeah, we do. It's x equals something with z's and numbers.
Very beautiful.
Yeah, so we are going to finish this. So the next, what's that, Nick?
Is that -3 7z, or is that supposed to be positive?
No.
That's a -3 7z and a -3 7s.
No, it's supposed to be addition because you moved it over.
Yeah.
Uh-oh, what did I do? Oh, you're right. Thank you. That is. Thank you, Nick. Good call. You're hired. Okay, so now we have to multiply all this. Okay, yeah, it's terrible. It's terrible, I admit it. So -74, I'm going to distribute these two. -74, Oh my goodness. 91st Z minus 10 91st plus 3/7 Z minus 3/7.
So now you combine.
Now you have to combine like terms. We've got two Z terms, but you need to find common denominators. And I've got two number terms, you have to find common denominators. Now, hold on a second, folks, watch me. I'm just gonna erase the ones I just wrote down. I know what my common denominator has to be. What do I have to multiply 7 by to get 91?
13.
13, right? I already knew that. Yeah, because we just did it for there. So I'm gonna go ahead and change these denominators right now. I'm gonna multiply top and bottom by 13. Okay, so that helps me out. So that'll be plus 39 91st Z, and then multiply times 13, top and bottom. And that'll be another minus 39 91st. We are so close to the answer now. And in fact, now that all the common denominators are there, this is pretty straightforward. What's our formula for x now? Negative 74 91st plus 39 91st. What's negative 74 plus 39? Negative 35 91st. See? Oh no, I just realized Shemaya and I'm getting close to the end of your visual range there. So negative 74Z plus 39Z, I believe that's negative 35Z, right?
Yes, that's
Okay. And then negative 10 91st minus 39 91st.
Negative 40.
Yeah. Now, I bet I know what all of you are wondering right now.
Now we plug that in.
Yeah, you don't have to plug that into anything. That's the answer. The answer is x in terms of z, y in terms of z. And at this point, if your employer had asked you to solve this system, you would go to your employer and you say, here you go, buddy. Whatever value of z you want, plug it in, and that will be your values for x and y. Right? Duh. No, I bet you're all wondering if that's the right answer.
No.
Is it? What does the answer key say? You all have the answer key? Moment of truth?
Number 12, 5.
Number
No,
5.
5.
Uh,
-7, 13 minus 5 over 13z is x, and then 5 over 13 plus 37 over 13z.
Yeah.
That's why? Oh, good. So was it correct?
Yes.
Oh, thank goodness. What do we have to do to our answer for x?
reduce it.
Simplify, because those are both divisible by 7. You guys, can you believe it? We actually got it right. Yes, Anna?
Like you put x equal, can we just plug in the y just like that? Like not even put x equal, like you did right there?
Like right here?
Yeah.
And just leave it?
No, I mean like can we just plug in the y, like the 37 and 13, like right there, like just the regular one, like on top of the x plus 2 top. No, bottom, x plus that one, yeah.
Yeah.
Can we just plug in that in there? Like the formula, whatever we got for the y equal? Or is it
Yeah.
easier?
You can plug it in right there.
Or would it be easier just the way you showed us?
Well, you can plug it in anywhere you like.
Yeah.
Yeah, that's up to you. Now, I tell you what, folks. What was that, number 5?
Yes.
Everyone cross out number 6 with a vengeance. All right?
That's so long.
One of those is fine. Now, on my math lab, I think I assigned you at least one of those.
Yeah.
I will not make you do more than one. Okay, so I'll double check my math lab tonight to make sure that there's just one of those. But it's well worth doing because it's just careful work. That's it. It's just very, very careful, slow work.
Yeah, because one number will totally go.
Yeah, if you're off by one number, bam, the whole thing is over, right? Okay. But it was a very helpful problem to do because it was still echelon form. We put it into echelon form. That allowed us to solve for y in terms of z, and then back substitute x in terms of z, and we did it. Okay. Goody gumdrops. Oh my gosh, we're almost done with echelon form. So we have 2 word problems to do. Now this is obviously the most exciting part. What kind of problem am I going to put on your test? A word problem. Because if I just gave you a matrix and I was like, go, well, like that's too easy. I just gave you the matrix. I want you to take a word problem and turn it into a matrix. Everybody's favorite. So, number 7. Unless anyone prefers number 8.
What the hell is do 8?
That's fine, we can do 8. Okay, so there were 400 people at a play. The admission price was $2 for adults and $1 for children. The admission receipts were $620. How many adults and how many children attended?
Is that the 2x and
Is that the what?
is that the 2x for adults plus the 1y equals 400?
Yep. So the first part is that you've got $2 for every adult and $1 for every child. And since this is dollars plus dollars, it has to add up to
$620.
$620.
It would be X plus Y equals 400.
Right. So keep in mind, folks, this first equation, we're talking about money. Yeah, dollars. $2 per adult, $1 per child, $620. The second equation is about the number of people, in which case the number of adults plus the number of children adds up to 400. Now, just knowing how to read a word problem and turn it into an equation, that's a skill right there. That's a skill right there, because what if you just wrote down the wrong system? It doesn't matter about your matrix skills because you're going to get the wrong answer. So skill number 1 is how to read a word problem and write down a matrix. Skill number 2, write down the matrix. So what is our matrix?
1, 1, 400. Oh, I'm sorry, I have it the other way.
Well, it's fine. Yeah, you can actually have these inverted if you want. If you have that one on top and that one on bottom, totally fine. And see, that's the beauty of matrices. It doesn't matter which one goes on top, you're still going to get the same answer. So.
We already had our second one.
Yeah, I know, we already have that one. Well, we already have that one. Geez, should we invert it?
That's what I was going to say. The way that I have it, we already have the diagonal ones.
All right, well then, I'm going to change it. Folks, we're flexible. We can just change it around. 1, 1, 400. And then 2, 1, 620.
0.
Yeah, that's true. We already have the diagonal ones. Yeah, so that's great. Good thinking. So now how do we get rid of this 2?
-2.
Yeah, we have to multiply the top by -2. And now see, this is why I'm talking about just pretend multiplication. I'm not really going to multiply the row by -2. I'm just going to pretend to multiply the row by -2. And I'm going to write down really small what the row would be if I did multiply it by 2. But I'm not really going to replace it because I like the row as it is. So now I'm going to keep the top row, which is 1, 1, 400. But I'm going to add these 2 rows together, my bottom row and my fake top row, to replace and make my bottom row. So what do we add? 2 plus -2 is 0. 1 plus -2 is -1. And 620 minus 800 is -180. Now, folks, why didn't I actually multiply that row times -2?
Because we already have our 1.
Yeah, because I'm going to want the 1 there anyway. But if that's confusing, if that's confusing, folks, by all means, go ahead and just multiply it anyway. If you really want to, multiply that top row by the -2 to get that, and then write down the row that you had anyway. And now go ahead and add the 2 together, keeping the top one. You keep the top one, and now add them and replace the bottom one. And now you just have to go back and divide the top row by -2 again. It's just a little bit of extra work, but if that's what makes sense to you, I want you to do what makes sense to you. And then we get back to 1, 1, 400, and 0, -1, -200.
Is this where you multiply the bottom row by -1?
Whoa, I just did that wrong. That was -180, wasn't it?
Yes.
Yeah, exactly. Now what do you do to the bottom row?
Multiply by -1.
Multiply the whole bottom row by -1, because that'll change that to a 1. So I have 1, 1, 400, and then 0, 1, 180. Because I did, in fact, multiply this one times -1. Are we in echelon form?
Yes.
Yeah.
Yeah, we are. Whoops. We are in echelon form, and unlike that previous terrible, terrible problem with all of those fractions, do we have any fractions here?
No.
No. But let's remind ourselves, what were our variables? This was x and y, x and y. So what's the one thing we already know? Y is equal to
180.
180. And therefore, there were what?
180 children.
180 children. Children. 180 children, right there. And now we have back substitute.
And then it turns into.
Now, of course, you probably all already know the answer. There were 400 people. And if there were 180 children, and there were 400 people, so there was 220 adults. But if you were to do the back substitution, legitimately, you'd say, okay, x plus y equals 400. You substitute, I know that y is 180. And then I solve for x by subtracting the 180. Now this is just scratch work, right? Now I'm just showing my work to find out what the other one is. So I have x is 220, y is 180.
But do we write on the line? Do we write 220, 180?
Well, now that's an interesting point. If you were to, I mean, yeah, if you were to write it as a coordinate, it would be 220, 180.
But this is a word problem. It's asking you how many adults.
Yeah, you would just answer the question. Yeah, that's an interesting point. Are they really talking about two lines graphed on a graph? Not so much. They really just want you to say adults, children. Yeah. Super. Blammo. Okay, I'm not going to solve number 7 with you, but we will write down the matrix together. Let's solve, because that's a skill in and of itself. How do you read a word problem and turn it into a matrix? So, how do we write this one as a matrix? Best Rentals charges a daily fee plus mileage for renting its cars. Barney was charged $102 for 3 days and 300 miles, while Mary was charged $185 for 5 days and 600 miles. So if we were to think about a matrix with this information, keeping in mind that we have one column, another column, and then the last number, or the last column, what do our different columns represent? What could the first column represent? Yeah, maybe days. What would the next column represent? Miles. And then the last column is the money. Now, Anna, you might be saying, now come on, what couldn't it be the other way around? But the thing is, it can't, because when we say 3 days, we're saying 3x plus 300y, and that together should be charged $102. So as soon as I know what the daily charge is, that's x. X is the daily charge. Once I know y is the charge for each mile. So it has to be days, miles, money, because those are your inputs. The cost for a daily charge, the cost for a mileage charge. Okay, so what's the other line? She was charged $185. Yeah, for 5 days and 600 miles. Now let's all remind ourselves, what does x represent?
X is the number of days.
3 is the number of days.
Oh.
Right, because it said 3 days.
Oh,
The daily fee.
The daily fee. Yeah,
Oh.
x actually represents the daily fee. That would not be a bad thing to write that down. X equals the daily fee. So when we're all done and we have our answer, x comma y, what is x representing?
a daily.
The daily fee. After all, what is the question? What do they charge per day? What's the daily fee? And what do they charge per mile? What's the mileage fee? Okay, so now how do we make this in a matrix? Because I actually didn't make that a matrix, I made that a system of equations. What's the matrix?
300, 2,
Yeah.
5, 600.
And don't you just love these numbers? They're nice, they're whole numbers. We feel like, okay, this won't be that bad to manipulate. Yeah, here's hoping. So I'm actually not going to do this one with you because the next section, section 2.2, is actually just echelon form taken a step further. So we're about to practice more echelon form in the next section, so I don't see why we would go ahead and spend time on this one when we can just keep going. We're going to continue practicing echelon form anyway. But now at least you're set up for number 8 that you go ahead and practice. The answer is in the back of the packet, and I'm sure you'll have problems like this on my math lab. Folks, first of all, you should all feel really good right now. If you don't feel really good right now, I'm forcing you to. You have to. This is good. We've covered a good chunk. And I bet you know what I'm reaching into my bag to give you. What do you think? Oh, how did you know that? Starburst. You thought it was going to be another fruit snack. Fruit snack. Oh no, it's a Starburst because you've gone the distance. Now it's just one Starburst for now. Come on, don't be greedy. I'll give you more later. But everybody, let's take a Starburst snack. All right. Now, I forget, what time did we say we were taking breaks?
7:30.
7:30? Well, isn't it? Oh, it's a couple minutes away from 7:30. So let's eat our Starburst and let's just look at the next section. So, section 2.2, the Gauss-Jordan method. Now, we've already been doing the matrices. I don't know why I wrote that, begin the matrices. We're already doing the matrices. We're actually going to do a couple of these questions right now. So, the first question, you guys already know how to solve. Write the augmented matrix for the system. What does that mean? Just write the matrix. So what would the matrix be for number 9?
9, 9, 27.
9, 9, 27, 8, 3, 19. Bammo, that's simple enough. I think they think that we don't know that yet, but we know that because we just spent the whole last section doing it. The augmented system for the number 10, that's going to be a larger matrix, right? So it'd be -2, 7, -246, 9, 7, 4, 81, 6, 6, -246. And that's going to be a big, massive matrix. Isn't that part satisfying? Just writing it down? It's so satisfying just to write it down. They're like, geez, why can't we just write it down? Why do we have to do all these row operations? Just writing it, yeah.
When is this augmented, does that mean putting the vertical line or no?
Well, by all means you can if you like. See, like folks, they put that line right there. I suppose they mean augmented by that because you have the x, y, z variable and then the constants that it's equal to. For our sake, augmented matrix is just what we've been doing all along. Yeah, augmented means you're not just, like, for instance, what if your matrix was just 9, 9, 8, 3? That would be a non-augmented matrix because you weren't looking at what the answer was supposed to be. You're just looking at the variables. But no, we're always looking at what the answer needs to be. So what we're doing is always the augmented matrix. Until section 2.5 when we don't look at the augmented matrix. Yeah. Okay, so number 9, number 10, no problem. Number 11, notice, is it already an augmented matrix? Yes. Is it already solved?
Yes.
Yeah. Is that in echelon form?
Yes.
It's in super duper echelon form. Yeah, I know, right? Why is this in super duper echelon form?
Because it's the ones that are in diagonal.
Yeah, we've got the ones in the diagonal. That's what makes it echelon form. But why is it in super duper echelon form?
Tells you what each variable is individually.
Yeah, because all the numbers are 0. Isn't that very helpful? What? Why does it matter that all the numbers are 0 other than the diagonal?
Because then you know x is 10, y is 2.
Exactly. I literally now know x is 10. And I know y is 2. And I know z is 4. So when you put it in super duper row echelon form, that's called the Gauss-Jordan method. So Gauss and Jordan are just two mathematicians who took echelon form and took it to the next level. They were like, hey, why just make these numbers 0? Let's just make all the other numbers 0, which is simply more work, right? That's it. Not different types of work. It's just more of the same. You just keep on manipulating until all of them are 0s, and then you just see the answer. How do you think computers calculate matrices? The Gauss-Jordan method. It uses the Gauss-Jordan method, which is super duper row echelon form. So that's our goal now. Now our goal is to have a diagonal of 1s, and everything else is a 0. Okay? That's the Gauss-Jordan method. Pretty cool, pretty cool. So let's see, is it already? No. Looking at these next couple questions, folks, 12, 13, and 14, they're just, well, it's everybody dance now. Let's go ahead and take a break. Everybody, very important. Everybody needs to stand up, go take a walk, go to the bathroom, get something to drink. You really need to stand and move and give your brain a break. Everyone come back in 10 minutes. So 7:40, we'll get started. Am I allowed to have a fruit snack? Oh boy, even I'm allowed to have one. Carmen, that's okay with you?
Huh?
It's okay with you that I have a fruit snack?
No.
Oh man. Carmen, I was very sad to see that you were tardy today.
Oh, I was lost.
Oh,
Keep
no, you poor
circling.
thing. Oh, you're looking for a parking spot.
No, I just keep circling on the third. Second.
Oh, out there? Okay, let me show you a trick. I'll show you a tip. First of all, where's the park? Yeah. No, but we put it in the calculator. Don't you still have to do all the operation?
Yeah.
Yeah.
Easier, I mean, you don't have to do all that much.
Well, that's certainly true.
Well, I mean, it's helpful, I mean, at least I know how to do it on paper.
Yeah.
Thank you so much for your shortcut.
Oh, yeah, you're welcome. Do you mean about the map or about the parking?
The parking.
Okay.
Do we have to do this packet too for homework or?
No. That was just for us in notes. I won't collect those. I call those interludes. They're just little lessons that I do. These, the official legit ones, I collect.
Are you, like, you collect them the same time, all three of them, or?
Yeah, I'll collect all of them on the day of the test.
Okay.
So we have practice test and no packet.
What do you mean?
This is the note packet.
Yeah,
The one
yeah.
that we're doing right now?
Yeah, for a grade?
But
Yeah.
Yeah.
Here we have like 3.
Yeah, notes packets and a practice test. And I think, did I already finish the practice test? Yeah, I already made the test and the practice test, so I just have to print it and give it to you guys next time.
So for no packet, we only have 3.
Yeah, you're gonna have 3, chapter 1, chapter 2, and chapter 17.
But
And we'll be-
right now we only have 3.
No, this one is not a notes packet for points. This one is just practice.
Oh.
This was just to teach you. The official ones are the ones that say like section 2,
Oh.
section 1.
Oh.
Yeah.
Got
So yeah, there will be 3. And then I will give you a practice test on Wednesday, since that's the end
When
of
is
our
our first exam? Isn't
next
it
week.
Next week, right?
Yeah, this is so fast paced. I mean, honestly, you guys all signed up for a world of hurt. Really, I mean, it is so fast. And I can't even slow it down. I can't be like, oh, let's just push the test back.
No.
Because the next test is just 2 weeks later after that.
Can we use the computer?
You mean during class?
Mhm.
I wouldn't recommend it. I think it'll just be a distraction. Why do you want to use the computer?
Because I'm bored right now.
Well, I mean, if you want to do it right now for the next, 5 minutes, you can. But then turn it back off when the class starts.
When you
just
get
keep
10
bored.
minutes.
Yeah, it's a 10-minute break.
I thought it was 30 minutes.
Oh, no way. No, 10 minutes. But it's not, we only get 10. You get 10 as opposed to 5.
True.
My allergies flared up and it's the worst feeling ever.
Oh, I rather have that allergies because when I get allergy, I get all reddish for my.
Yeah, but my eyes are starting to like itch and it's starting to get red. I'm already feeling it. I haven't been able to stop sneezing since I got here today. As soon as I got my car, I parked over here. This time.
Yeah.
And the other time I parked in the back wall. Like trees and everything else. That might be an issue.
It's alone. I don't bring my car. Let's see. I get dropped off.
Oh, dude.
I still haven't got my car. People really do want to.
Oh, people don't get it no more.
I mean, I don't have time.
I'm a little worried that I'm not gonna get down.
I didn't go out to be honest. That's how bad I'm in school. I don't go out. Hardly go out.
Oh, wow.
My friends used to be like in high school, so go out with my friends, but now they're like, when are you going out? Like, can I have school?
I don't know about
No, when I went to break down in Mexico. Oh, hell yeah. I loved it. Yeah, I actually did. I deserved a nice break. Away from school and away from the city. Because what? I go to Mexico from a small town. So. Yeah, they're still forever. You know, I think the one to vacation, one of the vacation.
I work at Amazon, so I really get 60 hours.
Wow,
I'm talking about living for a long time.
that is a lot. Only logged in too long now, so wait. What do you do your winter break?
What did I do? I basically prepped for this semester. You know, read the textbook, did all the problems. But no, I also hung out, just hung out with family and traveled a little bit. We went to Tucson, went somewhere else. Yeah, how about you? What'd you do?
I went to Mexico.
Oh, you did? What city?
I went to Guerrero, but I'm
Where?
from Guerrero, the state Guerrero.
Oh, Guerrero. Okay, the state. All right.
Yeah, but I'm from a small town, so I went to my town. It was nice.
Oh, cool. I've only been in a few places in Mexico. I went to Guadalajara for a wedding. One of my sister's best friends got married there. And then been to the FA and a couple other cities around the area. Like we went to the city that has the pyramids and some other places. Puebla. Went to Puebla.
Oh, Puebla.
Yeah. I think that's it. I know I went to a coastal town on the west coast for a cruise, but I always forget the name of it. It's this popular port town where cruises go to a lot. Gosh, what is it? I forget. So, but the FA was great. That's where I learned about mole. I had never had mole before.
Really?
Yeah, I know.
Really?
Imagine that.
It's so good.
It's so good. I know. Now I love it. All right. Everybody back? Yes, we are. Let's do it. So, we are commencing on the Gauss-Jordan method. And the good news is that most of it we already know how to do. It's just extending the idea of echelon form so you're getting even more zeros, which just requires more computation. But when you're done, it's wonderful because it just tells you the answer. So looking at number 12, 13, and 14, they're just giving us some terminology for what we've been doing. So everyone, let's look at number 12 together. What do they mean for number 12 when they give us a matrix, 1, 0, 2, and negative 1, 1, 3, and they say replace R2 with R1 plus R2. What does that mean?
The first row?
Wait, what?
Don't you go to row 2 and go to number one and use replace it.
Yeah, we're gonna replace row 2. So first of all, I'm gonna go ahead and rewrite this the same, but I won't write root 2 because I'm about to put something new there. I'm going to replace row 2 with
The addition of.
the sum of those 2 rows. So I'll go ahead and add these 2 together. That gives me 0, 1, 5.
Oh.
That's it. That's what their terminology means. It means literally replace R2. So you're gonna replace the second row. So erase it, get rid of it. And then what are you gonna put there? R1 plus R2. So that's the replacement method that we've been doing. How about number 13? It says replace row 2 by half of R1 plus half of R2. So this will take a little bit more work. First of all, since we're replacing R2, what should I do?
Put just R1.
Yeah, just put R1. I'm gonna leave R2 blank, right? Because I have to replace it. But actually, I'm gonna leave that for my next step. Okay, so here's the original matrix. What is it, -2, 2, and 12? Okay, so there's the original. What I'm gonna do is replace the second row, so I'm just gonna leave the first row. But what do I have to do? I have to take half of the first row and half of the second row, and then add them together. So this is gonna be some of my fake multiplying, okay? I'm gonna go ahead and take half of all that. So half of 2 is 1, half of 0 is 0, half of 2 is 1, half of -2 is -1, half of 2 is 1, half of 12 is 6. So I just took half of those. And those numbers, I'm gonna add them together and to create row 2. So what does that give us?
0, 1,
Negative.
no,
Yeah.
6.
Yeah.
Oh, 7.
So this is why it's handy to have this little tiny notation. That's when I'm fake multiplying. I don't know a better way to describe that. Should I call it fake multiplying? It's multiplying, but I'm not actually gonna make that my new row. So I'm multiplying to see what it is, but I'm not actually gonna replace that row. I'm just multiplying to see what it looks like. Okay, in both cases, why did they just tell us to do that?
So that we can get them or start getting them into.
Yeah.
echelon formation.
Yeah, so we can start working towards echelon formation. Specifically, what did they help us create? A 0 in the lower left-hand corner.
So will we keep the bottom? Do we have to work it further and keep the bottom row and divide the top row by 2?
Well, that would be the next step, wouldn't it? They would tell you, replace R1 with half of R1. But we don't actually have to finish solving this. They're just introducing us to their notation so we know what it looks like. So yeah, we don't have to do anything else at all. That's it, we're done. We're done with those 2. So what about number 14? How exciting, that's a 3 by 3 matrix. I realize it's a 3 by 4, but I'm calling it a 3 by 3 because the variable's a 3 by 3. This one, a little longer, 8, 0, 0, 6, 0, 6, 0, 6, and 0, 0, 2, 6. Oh, well, I mean, this is a silly one. There's not much to do there. Why are we replacing R3 by half of R3?
You get only 1.
Yeah, because you get a 1 there. Obviously, we would take half of both of those numbers. What would we do to row 2?
Divided by 6.
Yeah, well, you'd replace row 2 with 1/6 of row 2. So you divide both of those by 6. And what would you do with row 1?
Replace row 1 by 1/8 of 1.
Yep, replace row 1 by 1/8 of row 1. So you divide those by 8. So what would your final matrix look like?
1, 0, 0.
1, 0, 0, 3/4, 0, 1, 0, 1, and 0, 0, 1, 3. And that is Gauss-Jordan. That's the goal. The goal is to have your echelon of 1s, and you turn everything else into a 0, and then bam, you have your answer. So just looking at this, I already know that x is equal to 3/4, y is equal to 1, and z is equal to 3. Who likes matrix methods? Calculators and computers, right? I think it was Anna who said, first of all, you can do all this on your calculator, and that's true. You can program your calculator. You just put in a matrix, and then guess how you communicate to your calculator? With this kind of language. You tell your calculator, replace row 2 with R1 plus R2. And that's how you type all this into your TI-82 calculator, or you type it into an Excel spreadsheet or something like that. So that's why this kind of notation is important. All right. So the Gauss-Jordan method, just to show you a page out of your textbook, we can all now predict what's going to happen. Here's your system of equations that you want to solve. You want to turn it into the Gauss-Jordan form, which is an echelon of ones with everything else zeros. So they take your matrix, they do all sorts of row operations where you can see here they did 1/3 of R1 to replace R1. And they keep on doing manipulations until they get to here. Now everyone look at the final form. Does that look nice?
Yes.
It looks very nice. Did it look nice in the middle?
No.
Not so much. So you know that phrase, sometimes it has to get worse before it gets better? Have you all heard that phrase? Well, you start with a system, it gets worse, but then it gets better. Right? And then you just know your answer is x equals 3 and y equals 2. So this is really just computation heavy. It's not hard, it's lengthy. And of course, is it lengthy for a computer? No, not at all. So let's just think here. We've got 2 2x2, and then a 3x3. We definitely want to do a 3x3, and then some word problems, and then that's it. So let's do 1 2x2, 1 3x3, and then we'll do some word problems. Okay? Sounds like a plan to me too. Believe it or not, section 2.1 and 2.2 are both rather lengthy. 2.3 and 2.4 are like super fast. You're just adding matrices and multiplying. 2.5 will be medium. Yeah. Okay, this is fun, folks. You're doing great. And please, keep asking those questions. You help everyone by asking a question, because other people probably have the same question. So, use Gauss-Jordan methods. What do we write down? 6.
So our goal is to have a diagonal of ones and zeros on the other.
Exactly right.
Do they have different names for the ones that have the x and y versus the one that is just the answer? Like the rightmost, the 8 and the -8 and 28, do they have a certain name different from the elements?
Yeah, like this is
Or
the
are
x.
they all elements?
Well, they're all elements. This is the x column, that's the y column, and I guess that's the constant column or the coefficient column. This is technically the solutions, right? Once you get it in Gauss-Jordan form, these will be the answers. Okay, now, even though our goal is to have a 1 and a 1 here, do we want to go ahead and divide all that by 6 and divide all this by 9? No, because it'll create a lot of fractions, right? So the last thing we're going to do is divide to get everything, to get those numbers ones. Our real goal is to do what? Turn this into 0 and turn that into 0. That's our goal. This is very straightforward. That's our goal. We want to turn that into a 0 and that into a 0. So here we go. How do I turn this 2 into a 0?
Divide by -4.
Multiply that by a -3. That whole row by -3, which will give me -6, -27, 60, 84, -84.
See, yes.
So -84. And now I'm going to, what do I do to the first row?
Divide by -4.
The first row you do nothing, you keep it. Right? We're keeping it. Our goal, we're not doing anything in the first row right now. We're just trying to turn this into a 0. So now what are we going to do? We're going to replace the second row with the sum of both rows. Right? So what will my sum be? 0, -23, and -92. Did we do that right?
Yes.
Okay. Now keep in mind, for anybody, you see my little teeny tiny blue numbers? If you like that method, by all means, you can copy me and just make little teeny numbers to show you what that row multiplied by that number would be. But if you don't like that, you're like, Mr. G, that's not working for me. I really need to show it. I need to go ahead and put -6, -27, -84 there. And then, by all means, I can go ahead and keep the top row, and then I can add against 0, -23, -92. If that's what you prefer, that's what you should do. You know, because they both do the exact same thing. And honestly, did it take the same amount of work? There's a matrix, there's a matrix. Well, no, that was my first matrix. So technically, you would have to show one more matrix to get there.
It would depend on the audience.
It depends on your audience, too. And your first and most important audience is your own brain, because you're the one who has to solve these things. Okay, so now what do we do?
Now we want to get
Divide.
Yeah, now we want that to be a 0. Now let's just look real quick. Does 23 go into 92?
Yes. By
Oh my
4.
gosh, it does. So shouldn't we go ahead and divide? We might as well. We're not going to cause any fractions. The only reason not to divide is because you don't want to deal with fractions. But if right now we can go ahead and divide that off, I think we should, by all means. Because gosh, can you imagine trying to eliminate the 4 by multiplying and manipulating a negative 23? It would be terrible. So we'll go ahead and replace row 2 with negative 1/23 of row 2, which is just a 1 and a 4. So in that case, dividing was not a problem. If you can divide without causing fractions, go for it. Now what do we do? Yeah, now we do want to turn that 4 into a 0. So how do I cancel a positive 4? With a negative 4. So I'm going to take this equation, multiply it through by negative 4. I'm going to do it fake. So that's a 0, that's a negative 4, and that's a negative 16. And now I'm going to keep. Which row do I keep?
The bottom row.
Bottom row. And which row do I replace? The top row. So I'm going to add now my two numbers. 0 and 6 is 6. Negative 4 and 4 is 0. And negative 16 and negative is negative 24. Look how cool this was, folks. Did we do it? Did we get zeros?
No. Well, yeah.
Yeah, there where it counts. And now, what's the last thing?
Divide by 6.
Yep, we want to turn that into a 1. We just divide that row by 6. I'm going to go ahead and divide that row by 6. Oh my gosh, this worked out so nicely. There were no fractions. I fear I really terrified all of you with that problem over there. That was terrifying, wasn't it? You were like, oh no, what am I in for? So, this is called Gauss-Jordan. Barely any more work than what we were doing before. And now can we interpret our answers?
Yes.
What's x equal to?
4.
And what's y equal to?
4.
Yeah. Now, folks, you really want to be careful. Because right about now, you might get this sick and twisted idea in your head that you like this method better than those other methods. Right? This is almost starting to become attractive, isn't it? Like, this was kind of cool. We did some multiplication and addition with some numbers, and whammo, we just solved for x and y to tell us our coordinate in space, which was negative 4, 4. Not bad. Not bad at all. You might start to like this, which is fine. Just don't tell other people. You don't want to roll up to a party and be like, hey, guys, I really like matrix methods. You'll get kicked out of the party, right? I'm just kidding. Matrix methods are great. Okay, well, we did it, folks. That's the end of the problem.
That's it.
Is it? Are we correct? Is x equal to negative 4 and y equal to 4? How do you know?
Plug it in.
You can plug it into the original equation and see if it makes it true. So let's find out. 6, that's negative 24 plus 16. Negative 24 plus 16 is negative 8. That worked. And then negative 8 plus 36 is 28. All right, there we go. We did it. It really did work. How else do you check to see if you're correct? You can put it all in your calculator, ask your calculator to do it for you. You can check the answer in the back, right?
Oh.
All the answers are in the back. So you can just check your answer. Okay.
I'm a little bit lost. What was the difference between two?
Wait, Carmen, say that again.
That was the difference between two. One is matrix, one is the Gauss-Jordan.
Oh, yeah. So what's the difference between Gauss-Jordan and echelon form? Here's echelon form. So I'm just going to show you the echelon form. Echelon form, when you're done, looks like this. That's echelon form. Gauss-Jordan, when you're done, looks like this. What's the difference?
Okay.
They both have an echelon. They both have a 0. So what's the difference between echelon form and Gauss-Jordan form?
Use another 0.
Yeah, you other than the diagonal of 1s, you turn everything else to 0s. Can you turn these to 0s?
That's right.
If you have the Z, right?
Well, maybe if there was a z variable or something else. But I mean, what would that even mean if those were 0s? It would mean that x is equal to 0 and y is equal to 0. So no, you can't force those to be 0s. Those are the answers. You know, when you're all done, those are the answers. So it's only going to be 0s if that's what the actual answer is. You can't force it to be the case. Okay, very exciting. Should we do another one? No, I think not. I think we should try the 3 variable case, the 3 by 3. Now, when you see a 3 variable system, what is the first thing you should do? Cry. Right? Maybe cry, get it out of the system. Have a good cry, maybe hug it out with somebody, but then get back to the board and keep going. So what's our matrix?
119.
Yeah. And 2, negative 3, 4, 7, and negative 4, 3, and negative 2. Now, it probably helps if you remember your goal. Our goal is to have a diagonal of 1s and everything else 0. But you're not really going to turn things into 1s until the end. Right? You wait until the end to turn that diagonal into 1s. Right now, we want to focus on turning that into 0, 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 that into 0. So how many different things are we doing? 1, 2, 3, 4, 5, 6. There's 6 different operations we have to do, at least, to turn all those into zeros. And then when we're done, we have that diagonal of numbers, which we just divide through, and we turn them into 1s. That's the big picture. So, what do we do? We should just start from the left to right. We read from left to right. Let's go from left to right. Let's cancel out that 2. How do we cancel out the 2? Now, write teeny tiny like me, folks. We're going to try to do this without taking a whole page of work. So, how do I cancel out a positive 2?
Divide by.
We want to cancel it out to 0, so we're not adding or subtracting. Wait, I'm sorry. Yeah, we are adding or subtracting. Sorry. You need a negative 2. So let's turn this positive 1 into a negative 2. We're going to multiply the whole top by negative 2. So up top, I'm going to write negative 2 dot, and that's going to remind me to multiply the whole top equation by negative 2. So that's negative 2, negative 2, negative 2, negative 18. And keep in mind, what am I doing to the first row?
Leaving it alone.
Yeah, we're leaving it alone. We're not doing anything to the first row.
Changing the form.
Yeah, well, we're about to change the middle row. Yeah, we're about to do row 2. So I just created all my negative 2's there. So now let's go ahead and add my tiny numbers plus the middle row to create my new middle row. And what do we get?
0, negative 5,
0,
2,
negative 5,
negative 9.
2, and yeah, negative 9. Really nicely done. We already have a single 0. Now, the reason I said, if I said it, to make the tiny numbers up top, because now I'm going to make a new row of tiny numbers on the bottom. Right? So now, how do I cancel out a positive 1?
Negative 1.
With a negative 1. So now I'm going to multiply that same top row by negative 1 all the way across. I'm going to write it down to tell my brain the right numbers. That's a negative 1, that's a negative 1, that's a negative 9. And now I'm going to combine those two. And notice this piece of technology I'm using in my left hand. It's called my fingers. I'm going to use my fingers to make sure that I'm adding the proper numbers together. Yes, Anna?
Isn't negative 11 instead of negative 9, 8, negative, right? You're subtract negative 18 minus 7, I mean plus 7?
Oh, you're right. Negative 18 plus
Yeah.
7 is negative 11. Thank you,
Yeah.
Anna. You're hired. Okay, so now we're going to go through, replace the third row. So what do we get? 0, negative 5, 2, negative 11. Whoa, what just happened?
We got 2 zeros.
Yeah, this actually looks like this is going to be a special kind of system. I didn't realize that this one was going to have a surprise sudden ending. These 2 rows are now the same.
Yeah.
So if I replace, if I keep the first one and the second one, and I replace the third row with the sum, sorry, not the sum, but the difference of these 2. What if I subtract them?
0 all the way
It'd be
down.
0, 0, 0, 0, 0. Well, that's a problem. That means we no longer have a solution for z. However, what does 0 equals 0 mean? Yeah, it's a true sentence, but it doesn't actually tell us what z is. So this now is actually that terrible problem that we did a second ago, where because this whole bottom row canceled out, we have a 2-equation matrix in the variables x, y, and z. And so you would solve for x in terms of z and y in terms of z.
So Z
What?
goes more into Z then.
Z canceled out. That means that z can be anything. Yeah. Well, yeah, z canceled out of the equation.
Yeah.
And anytime a variable cancels and it leaves you with a true statement, it means that that value can take on any value.
I'm still confused. How do you get the 0? Do you use multiple?
Here, what I really did is I took
Yeah.
this row and I multiplied it times negative 1. That gave me
Oh.
0, 5, negative 2, and positive 11.
Yeah.
And then I added those together,
And that just.
and I got zeros.
Oh,
Yeah.
So, and the bottom row being means that Z can be anything.
Z can be anything. Right. So now, folks, we would go ahead and say, since Z can be anything, we go ahead now and stop, and we interpret our solution, because we're actually done. I mean, we could finish doing the Gauss-Jordan method of turning everything into zeros, and actually maybe that's what we should do. Yeah, let's
Can we
finish.
try to do that first?
Yeah, let's do the Gauss-Jordan, let's finish it. So ideally, we still want to turn these into zeros and that into a zero. Well, we can do it. We really can. So, where should we begin? These both have to be zero. But unfortunately, we can't turn them both into zero because that's already a zero. Let's turn this one into zero first. There's a little bit of play here. Let's do this one first. So,
Wait, hold on.
yeah.
Just a question, the one before we added the sum?
Yeah.
Is there a step we should do prior to that, before we turn them off to zero?
Multiply, so you multiply the middle row by a -1.
Yeah.
So that when we added row 2 and row 3, we substituted row 3 with the sum.
Yeah. That's how I got the zeros.
If I'm saying, since we're not gonna do it that way yet, or we still should just leave it that
Yeah, let's leave it this way, because for sure that bottom row is zeroed out. Yeah, that is important. So now, though, let's continue putting zeros everywhere else that we wanted the zero. So let's get rid of this 1. How do we turn that 1 into a 0?
Multiply 5.
Yeah, we're going to multiply that whole row times 5, so that'll be 5, 5, 5, 45. And so we keep the bottom, we keep the middle, but then what does our top row become? Yeah, so 0 plus 5 is 5, that's a 0, that's a 7, and that's a
34?
Yeah, 34.
I thought we should keep the first row the same.
Well, I mean, oh, you mean not? But the thing is, we just replaced the first row. We replaced the first row with the sum of row 1 and row 2. Because our goal was to turn this into a 0. So we are changing row 1. And the only way to turn that into a 0 is to add these 2 rows together, the blue and the black. And that way we have this new row 1. The reason we wanted that is to have a 0 right there. So just flip it?
No, do the second row as first row. You are seeing the second row as the first row and keep the same, right?
Yeah, we're keeping the second row now to replace the first row. Okay. Okay, folks. So we did it. I think that's as far as we go in terms of turning these things into zeros. Yeah. You can't, we could try to multiply, turn this into a 14 and that into a 14. But as soon as we do that, we're going to ruin these zeros. And those zeros will go away. So it's like you can't get rid of everything. So here's what we have then. We have 5x plus 7z equals 34. And we have negative 5y plus 2z equals 11. And those are our last 2 equations. So we'd have 5x plus 7z equals 34. And negative 5y plus 2z equals negative 11. But what we really want to do is solve for x and solve for y. So how do I solve for x in the first one?
Move the 7z over and
You move the
divide by
7z
5.
over, so 5x equals negative 7z plus 34. Divide everything by 5. So here we go. We have x equals negative 7/5 z plus 34/5. That's what x will be depending on your choice of z. Because z can be anything, and we know z can be anything because the bottom row is zeroed out, you can only solve for x in terms of what you choose z to be. So that's my solution for x. Try it.
Yes, is there a way that we can almost start this whole problem? And before you had changed all of them to 0, is there like a step that we do like one at a time to turn it into zeros and ones?
Well, we did do it one at a time. Oh, one at a time?
Yeah.
Well, you're right. I did do 2 steps at once, didn't I?
Yeah, like before you got to the one where it literally just lost me completely. That one, when you zeroed all of them, when we switched from going from 1 to all the way to the third being changed.
Yeah.
To the third row, because we were changing just the second row. And-
Right, so
And not adding yet?
you're okay with where we were here?
Right.
Okay, so right here, let's just go ahead and say that I wanted to turn that into a 0. How would I turn -5 into a 0?
So
Add 5.
add 5, right?
Yeah. Well, so I need this to actually not be a -5, I need it to be a
Positive.
+5. So that means I have to multiply it by -1. So I multiply the whole row by -1. So -1 times 0 is 0, -1 times -5 is 5, -1 times 2 is -2, and -1 times -11 is +11. And then I add those two together to create my new bottom row. So what's 0 plus 0?
0.
And 5 plus -5? That's the 0 we wanted.
Right.
And now -2 plus 2?
I'm sorry, 0.
And -11 plus 11? I'm sorry, -11 plus -11. 0. So it was just a consequence of that row operation that they all happen to turn to zeros. And as soon as they're all zeros, that means that 0z equals 0. And you can plug anything in for z, because 0 times anything equals 0. So that tells us that z can be anything. And then it's at that point that we say, okay, well, we just have to solve for x and y in terms of z. Okay, so everybody, let's finish the last one. The second equation was going to be, what, -5y plus 2z equals -11? So again, you just have to solve for y. So you'd move the 2z over, so -5y equals -2z minus 11, and then divide everything by -5. And now we know that y is equal to 2/5 z plus 11/5.
Can you just write everything on top and then put a line with the bottom for 5?
Oh, sure, yeah, you could do that. -2z minus 11 divided by -5? Yeah. I'm pretty sure my math lab will accept it either way. Okay, well, folks, that was surprising. I didn't realize, just looking at it, that was going to happen. We were doing number 17, right?
Yes.
Uh-huh.
Yeah, we did copy it down, right?
Yes.
Mhm.
We copied it down correctly?
Yeah, it's correct in the back.
Oh, that is the answer?
Mhm.
Okay, so we actually got it?
Mhm.
Oh, okay, gumdrops, folks, so we really did it. Now, let's just say that we got to here, and it didn't all become zeros. We would have just kept on our merry way, turning everything else to zeros until we finished. So I think what we really need to do now is a 3x3 where we finish the Gauss-Jordan method. So we could either do 18 or 19. Well, you guys check.
18, I just have to say, looks like that in the back.
Oh, 18 does? What does 19 look like in the back?
It looks like it's all the way.
What?
It looks like it's all, oh, nope, never mind.
That one
No
also looks that
solution.
way?
It has no solution.
Oh, not even a solution for that.
Mhm.
Okay. I tell you what, yeah, guys, cross out 18 and 19. That's fine. Boy, Anna, you're a winner there. You're like, can I cross it out? Normally, what does the teacher say? No way, still do it. No, that's fine. Cross them out. But we do want to do one that has a solution, and I'm guessing the word problems will. I think the word problems will have a solution. So, will you look at the answers for 20, 21, and 22 and just make sure, choose one that has a solution? Okay,
Yeah.
good. Now keep in mind, folks, these are solutions. They are solutions. It just means that there's infinitely many solutions. It's kind of like it means the lines are overlapping. There's more than one solution, and that's what that looks like. But we want one that has one solution, right? We want to feel satisfied. One solution. So, which word problem? Barges from ports X and Y. Okay, so you got barges going different places. A chemistry department with different percents of solutions, or Linda investing money into different percent solution or different percent investments.
I say number 20 before percents.
What's that?
I say number 20 before we do the percent.
Now that's interesting. Julie would like to do number 20 because it doesn't have percents. And of course, what am I going to say?
You want to do the percent?
We should do number 20, one of these because it has percents, right? Because I want you to see that it's not as terrible as you think it's going to be. So, what's that? I was actually going to say 22 because this is a mathematical analysis for business class. So number 22 is actually about business. Let's do number 22. So, Linda invests $25,000 for 1 year. So, what do you guess Linda's about to do? Is she going to take all $25,000 and put it into one account?
No.
No, she'll probably put it in multiple different accounts with multiple different interest rates. How many accounts is she putting it in? Three. Of course she is. Thanks, Linda. So, Linda We probably, so what are our different columns gonna be? The 5% column, the 6% column, and the 8% column,
Yes.
and then the answer column. So we kind of already have an idea of what, how to set up our matrix. We also have this number column down there at the end. And so it says, part is invested in the 5%, part in the 6%, part in the 8%. The total income from all three investments is $16,000. Yeah, that's total income.
X, so would it be X plus Y plus Z equals 1,600?
Right, well, it's going to be the total income. Now, here's our first question. The total income. That doesn't mean how much money she has total at the end. Because if she invests $25,000, how much is she going to have at the end? Maybe $28,000, maybe $30,000. But they're saying the total income is $1,600. So what they're really talking about is just the interest, right? So they're just saying the interest from all three is $1,600. So the first thing we would note is that however much we put into the 5%, and however much we put in the 6%, and however much we put in the 8%, that total interest is going to be $1,600. But we can't just put X, Y, Z, because what do X, Y, and Z represent? X is the amount of money in the 5% account. Y is the amount of money in the 6% account. And Z is the amount of money in the 8% account. And X plus Y plus Z adds up to 25,000. That's how we're defining our variables. So what we have here really is 0.05X plus 0.06Y plus 0.08Z. That equals 1,600. Now I realize I'm not really making a matrix right now. I'm making a system. We should write the system first before we just plug numbers into a matrix. So the first thing that they're telling us is that 5% of the money you put into that account, and 6% of the amount you put into that account, and 8% of the amount you put in that account, all of those are interests, and when you add them all together, you should get 1,600 interest. Is that an okay equation? Okay, let's keep going. Now, the next thing she says is that income from the 5 and 6% is the same as the income from the 8%. Yep. What does that even tell us?
Oh crap.
What's that?
Oh, I said, oh crap.
So how much total interest did we get? 1,600. And they're telling us that the interest from the 5 and 6% is the same as the interest from the 8%. These two values are equal, and they add up to 1,600. If I have two amounts that are equal and add up to 1,600, how much is each one?
800.
800. Okay, so now we know that the amount from the 5% plus the amount from the 6% adds up to 800. And we know the amount from the 8% is also 800. Are those two equations okay? Now that took some thinking, didn't it? We had to stop and interpret the word problem to even know what they were telling us. That did take a little insight to say, okay, since they're the same amount, they must add up to 1,600. They must be equal, so they're 800 each. What numbers go here, here, and here? Zeros. Right? Because those are not part of the equation. Well, we now have a matrix that we can manipulate and solve. Now, keep in mind, we need a diagonal of 1s going down right here. And look at this last equation. Where's the only place that could be a 1? This last one. So this is a good one to stay in that row because we want a 1 right here, and we want a 1 here, and a 1 here. So that's fine. We've already got some zeros here. We've already got that 0 there. We're working our way towards echelon form already. So this is going to be our ultimate echelon. Yep. And we'll start working on it. So now, what's the part about this that you don't like? All those decimals. Yeah, what can we do?
Multiply them by 10.
Multiply them all by just 10?
100.
By 100. If we multiply them all by 100, we get rid of all the decimals and we turn everything to regular numbers. So let's do it. Now we're actually going to write down a matrix. Everybody move your decimals twice. So this is 5, 6, 8, and 1, 6, 0, 0, 0, 0. And then 5, 6, 0, 8, 0, 0, 0. And then 0, 0, 8, 8, 0, 0, 0. Is that correct? We got rid of the nasty decimals. And now we just need to start turning this into row echelon form.
Can we just take that center row and just multiply by a negative number?
Take the center row?
Yeah.
Yeah, to do what?
Well, but then I'll come up 0. Never mind.
Well, yeah, we are going to want to manipulate a lot.
I think you're missing 0.
Yeah.
8,000, 80,000.
I did miss a 0?
Yes.
Yeah.
That's 80,000? Is it 2 more zeros?
Just one.
Oh, yeah, there we go. Oh, yeah, obviously, because 80,000 plus 80,000 is 160,000. Okay, thank you, guys. Okay, so what should we do? I always just start at the upper left. You know, start from left to right, and you just start working from left to right. So we know that we want this to be a 1, but we're not going to divide by 5 yet. And we want this to be a
0.
0. So let's go and make that a 0. I'm going to go ahead and multiply this whole top row by what? -1, so that way it's -5, -6, -8, and -160,000.
It doesn't matter if you multiply the top one and the middle row.
No, but keep in mind we want to replace this row.
But can you multiply that one and still replace it though?
Yes, you could. Yeah. So, keeping in mind we're going to replace the middle row. That means I'm going to keep the top. And now I'm going to go ahead and replace the middle row. So, 5 and -5 is 0. 6 and -6 is 0. 8, -8 and 0 is -8. And then -160,000 and 80,000 is -80,000. Okay? And at this point, we still just have.
It cancel again.
Hmm?
Doesn't the 0 go away?
Gosh, does it? Wait, did we say that this one had one answer? Number 22?
22, yeah, it has 10,000 at 5%.
It has 2 answers. It has 2
And
answers.
10,000 at,
It does have 2 answers.
Yeah, but not a third.
Oh, well, okay, folks. And you know why? Because, like, for instance, I could do something silly and put -$1 million in that account, and then put money in these 2 accounts that balance out the -$1 million to come out to be 25,000. So there could actually be infinitely many solutions, but a lot of solutions won't make any sense because you can't put a negative amount of money in there. To give you an example, how much total money are we dealing with? 25,000. So if I wanted to, I could put no money in the first account. No. I could put -5,000 in the first account, 5,000 in the second account, and then 25,000 in the next account. Would those all add up to $25,000? Yeah, so that is technically 3 numbers that add up to 25,000. But does it make any sense to put a negative amount of money into an account? No. So actually, this problem does have multiple solutions. It is true that this is going to cancel out. Well, let's run with it. Ah, I'm so disappointed. Okay. I was really hoping that there would just be one answer. It's okay. Let's just keep doing it. Because this is a really important example for you guys to see. So now what are we going to do? And this is helpful, Shemaya, because we're about to do the thing that happened last time.
Rewrite it and just put the whole bottom row with zeros.
Yeah, right now we want to cancel out this row. Well, what we really want to do is, let's see, that's already a 0 and a 0, and that's already a 0. We would technically want to turn that into a 1, but then we would want to turn that one into a 0. But we might as well, since we know it's going to cancel, let's just do it. So we now have 5, 6, 8, 160,000. And then we're going to replace the bottom row with the sum of row 2 and row 3. Is that correct? We're going to replace the bottom row. So keep the middle row. And then replace the bottom row with the sum of row 2 and row 3, which is just all zeros. Now again, anytime you end up with all zeros, that means 0 times 0, 0 times z equals 0, which is always true. So z can technically be anything.
I have a question with that 8 and
Yeah.
-8.
Yeah?
Oh, nothing. Never mind.
Okay. All right. Well, we can.
It can be anything in the solve for y.
Actually, I'm sorry. That was wrong of me to jump to the conclusion that z could be anything. Let's finish with this row. What could we now do since there's just one number and the number at the end? What would we do?
Divide.
Yeah, we'd go ahead and divide that out by the -8, so we can easily turn that one into a 1. And so what do we get?
Let's see, it's what, that's.
So we'd have 5, 6, 8, 160,000. And then the next one would be 0, 0, 1, and what? 10,000?
Yes.
Okay, and then the other row is just all zeros. Okay, so actually what this tells us is that Z actually does have to be $10,000. We just finished that one. Z has to be $10,000. It's this other one that's a little more flexible in terms of different possible answer choices. So what we would do, I'm sorry, I don't mean to overly complicate. I don't want to lose you guys on this. And unfortunately, this one was, okay. So where should this row be since the number 1 showed up here?
The bottom.
It should be the bottom one, right? So let's, what's that? Yeah, you can totally flip them. So we've got 5, 6, 8, and 160,000. And then we've got our 0, 0, 0, 1 with 10,000. And then the other one is all zeros. Yeah.
That makes a little,
It what?
it makes a little more sense.
It does make a little more sense because we did want to get that diagonal there with the 1s.
Yeah.
Okay, now, what else can we possibly turn into a 0? Can we turn the 5 into a 0?
No.
6? No. 8?
Yeah, I guess.
You can multiply this times -8 and then add it to that one. And that's what we'll do. So everyone, let's do it. Multiply that whole bottom one by -8, which ironically, we just had that there a second ago. So that was -8 and -80,000. And so we are keeping the bottom row, and we're also keeping the middle row, but we're replacing the top row with the sum of R1 and R3. So what do we get? 5 plus 0 is 5, 6 plus 0 is 6, but 8 plus -8 is 0, and 160,000 minus 80,000 is 80,000. Oh my gosh, this is so exciting. I know it's confusing to have that row of zeros there, but let's just continue on course of getting rid of, turning everything to zeros that we can. We're now done. We now have that Z is equal to 10,000, and 5x plus 6y is equal to 80,000. Now, folks, you just told me at the back of the book that Z was 10,000.
Yes.
Mm-hmm.
What were the two answers?
Is 10,000.
Yeah.
So $5,000 at 6%. So 6% is on Y.
Yeah.
So Y is 5,000 and X is 10,000.
Okay. What was the other answer?
That's why I was trying to figure out how you guys were looking at there was 2 options. I don't see 2.
Oh, there's just one?
That's all. That's all I.
Okay, so there is only one answer. But something about that didn't work out.
Yeah.
We clearly have that answer for Z. Do you think that we could have made a mistake at some early point? It was $25,000 that we invested. Where is there?
Never used the 25,000 in our. Is it just extra information?
That's a really good point. We never did use the 25,000. Should it have been? I mean, I suppose.
Yeah, because it says part is invested into a 5%. So wouldn't the top one be actually the 20? So 0.05x plus 0.06 y plus 0.08. That first one equals the 25 because part of that 25 is going to go into the 5%. Part of it is going to go into the 6%, and part of it is going to go into the 8.
Oh, well, you know what, folks? You're absolutely right. But it wouldn't be any 0.05s. What would the equation be if x plus y plus z equals 25,000? It would just be 1, 1, 1. Folks, I'm sorry, I led us down the wrong path on this problem. I was thinking that everything was going to be percents and everything, but it's not. There would have been one equation that was 1, 1, 1, 1, and then 25,000. That makes a lot more sense. Because then, so I tell you what we're gonna do is, let's just finish writing this system down the way it should be, and then we won't spend any more class time on it. I'm gonna write up a full solution and I'll post it online so that you guys can go back and look at it later. But let's go and write it down what it should be. What would our first equation be? 1, 1, 1, and 25,000.
Yes.
There we go.
Yeah, really good point. We never even use that information. And that's probably why one of these equations canceled out. And you know which one of the equations canceled out? The two equations that were half and half of the account. Okay, so then the other one would be the 0.05, the 0.06, the 0.08, and that added up to 1,600. Yep. And then the other equation would be,
Could we have
Four lines?
what's that, Mike?
Would it be 4 rows?
I don't think there's gonna be 4 rows, because we already know that if we put both of those, they'll cancel out.
We can use one or the other.
One or the other. Because they cancel out, it means technically they represent the same information, which obviously they do represent the same information because they were both the same information, weren't they?
Yeah, over here on the 1, 2, 3rd one.
Yeah, they both ended up being just 8 and 80,000, 8 and 80,000. So we only need one or the other. So which one would you rather do?
0.08.
Yeah, just the 0.08 to be half.
Okay.
Right.
Yeah.
That does make a lot of sense. Folks, again, I'm very sorry that the fact that I wasted that we lost that class time together. I'm gonna make up for it by posting this solution online and essentially, allowing you just to look at it and see it. That way we can use our class time to move on to something else. But do you now know how you would solve this matrix?
Yes.
What's the first thing you would do?
Mm,
Would you still want to get rid of all those decimals?
yes.
Probably. So we're still gonna get rid of the decimals, 1, 1, 25,000. And then multiply or remove the decimals twice, so 5, 6, 8, 1, 6, 0, 0, 0, 0. And then again, move the decimal twice, so you'd get 8 and then 80,000. Okay. We are really sure now that that's the matrix we should use because it used all of our information. And now you would just continue on with eliminating as much information as you could. Should we do it or not? Right now.
I don't
think
know.
we should move on.
I got enough room.
I know that room.
Okay, well, that's
And then
fine,
it'll
that's
be so
fine.
like,
Okay, well, that's totally fine. So, like I said, I'll post that solution. What about just setting up the other two problems? Okay, how do we set up the other two problems? 'Cause
oh yeah, there we go.
the actual row operations, that takes up a lot of our time, whereas I think you can do it. But how do we set up the problems? So, how do we set up number 20?
Okay, so it says start as one port X, Y went to cities A and B. X sent 30 barges, and Y sent 8. That's the total, so X plus 5.
So, we've got 2 ports and 2 cities. So, would it be fair to say that one, like for instance, it could be port X for the first equation and port Y for the second equation, and then it's sending it to cities A and B, and then the shipping costs is how much it actually costed. Now that's just a possibility. I'm just throwing out a possibility. Let's read the problem and see if that fits. So barges from ports X and Y went to cities A and B. So X sent 30 barges total, and Y sent 8 barges total. A received 22 barges, B received 16. Shipping costs of $220 from X to A, $300 from X to B, and $400 from Y to A, and $180 from Y to B, and $86.80 was spent. So how many barges went where?
Uh-huh.
Right. So that's a lot of information right there, right?
AC's up too.
X sent 30 barges.
You just throwing us out and just. That's all right.
Right. Okay.
Show hands, anybody who works for a shipping company? No? All right.
Yeah. Now, we just want to think about how do we put this information into, say, some sort of equation? One thing that helps is to look at the question. How many barges went where? So for sure, we're only going to have two variables, x and y, right?
Yeah.
And so x should represent the number of barges, right? And y is also going to represent a number of barges. And it's saying barges from port X. So could we say that X represents the number of barges that left port X?
Sure.
And Y represent the number of barges that left from port Y?
Sounds good.
Right. So that might not actually be that port X and port Y that I labeled that correctly on my first go around. It could be that that's what our variables are going to represent. So let's put in our variables here. And now let's see what happens. So barges from X and Y went to cities A and B. X sent 30 barges total, and Y sent 8. See, A received 22, B received 16. Yeah, how do we put this information into a matrix?
Can we skip it?
Well, we don't want to skip it, but there has to be a way for us to, by looking at this, think about how to put it all into information. So shipping costs are $220 from X to go to A.
I think it should be 3 lines.
Do you think so?
Mm,
You got 3 different.
Yeah, you have 3.
Now, let's all pretend that we're all sitting at home right now. What would we do?
skip.
Yeah, not skip. Well, then where's my, oh, I closed out of it. Because we can just go ahead and find this problem.
Wow,
Wait,
looks like
math class
Mm-hmm.
will
4.
have that?
Hmm.
Oh, God.
Does it really? Is that it?
I think so. So now here's 218. And we're going to our homework.
Does it look like there's 4?
And we're in chapter 2.
Does it look like there's 4?
And then it's probably around,
Wow, we have 40 questions?
Hmm?
40?
what, is that more than the last one, 40?
Yeah.
Oh, yeah,
I mean,
yeah,
that's
but for
easy,
instance,
yeah.
folks, look at this question. All it says is write the augmented matrix.
Yeah.
See, that in and of itself is not a hard question.
Yeah.
You're just
But is
plugging in the numbers.
Is there only one of those?
One or two.
Write the system of equations associated with. So here you're taking the matrix and turning it into a system of equations. So let me see if I can get us.
You're right, just one of those.
Here's the
That's
guy.
only one.
So far, these problems are all
Except for the
simple
one
compared to what we're trying. See, right now we're trying the big ones.
Does it look like 4 meters?
Well, you know what,
So
folks?
those are adding, subtracting, we haven't
Yeah.
gone through those.
Yep, you know what this means? I've only given you one, folks, there was only one word problem
Yeah.
in here, and it's about a furniture factory, and it is not at all like this one.
Okay, that's good.
So you know what that means, what we can do with this one?
Cross it out?
Yeah, we can cross it out.
Woohoo!
However, I'm still gonna post the solution online for you guys later tonight.
For number 20?
Yeah, for number, yeah, the one that we were just.
Yeah, can we go through the math for that kind of question? Because I see you got some subtracting, and that's what I'll be struggling at home, trying to figure out what is we doing.
But isn't that the easy one to add and subtract on?
Yeah, let's go ahead and do those right now so that you can see that it's not terrible. Okay, so for now, folks, especially because of time, I'm gonna leave these, and maybe in the next class, we'll do one of these that I carefully choose that's gonna have a really nice clean solution. For now, let's look at section 2.3. Honestly, section 2, 3, and 2.4, part of me thinks should have been the first sections because they're so simple, they build confidence.
That would be nice.
So, how do you add a matrix?
It's at the same,
Yeah,
the
same
elements in
one.
the same spot.
Yeah, exactly. Term by term by term in the same location. So what would that sum be in the first problem?
1,
3, 3.
Yeah.
Yeah, you would get 1, 3, 4, and 6. Right? Is that fair? So matrix addition, you just add each term by term by term.
Well, that's nice.
It is nice.
Second one you can't do because they're not in the same.
Yeah.
Yeah. Number 24 you cannot do. There is no solution for 24 because they're not the same matrices. They have to agree completely. Now let's before we get too far on here, just adding things. Well, no, go ahead. So number 24, no solution. Number 25, what would you do? You subtract term by term by term. Now you have to be very careful because you're subtracting. You might want to say it out loud and in your head.
So it'll be -3.
So -1 minus 2 is -3. -1 minus 1 is -2. And 0 minus 7 is -7.
No, it's not.
That's why.
It's
2.
minus
It's
one.
2 minus 1.
Oh, 2 minus 1. I see, I looked at
Yeah.
the wrong spot. Yeah, 2 minus 1. And then 0 minus 7 is negative. So that's 2 minus 1 is just 1. Thanks, folks. And 4 minus 4 is 0.
Wait.
And 6 minus 4 is 2.
And -6.
And -4 minus 2 is -6. Yeah.
Yes.
Okay, so subtraction just works term by term by term. Shemai, did that work?
Yeah, I can't do that.
So here, Shemai.
I don't follow like that.
And it's also very helpful to use your fingers, folks. So -1 minus 2 would be the first entry. And then 2 minus 1 would be the next entry.
If
So
you
term
need,
by term by term.
and if you need further help, you can put X, Y on top.
Yeah, you could even label them.
She skipped the problem.
Now, let's talk about the sizes of matrix, okay? When we label the size of a matrix, size is always given by row by column. The number of rows times the number of columns. And it's typically written as M times N. Those are just the variables that tend to choose. So what is the size of this matrix? How many rows?
2. Which one are you talking about? 2?
Oh, this one right here, yeah. 2, and how many columns?
By 2.
2. So this is a 2 by 2 matrix. Now 2 by 2, they're both the same number, but you have to keep in mind, it goes rows and then columns. Okay, what's the size of this matrix?
3
3
and by 2.
by 2, right. And so what's the size of this matrix? 1 by 2, 1 row, 2 columns. And what's the size of this one? 2 by 1. So see, these sizes were not the same. So you cannot add them, you cannot subtract them. So in order to, and see, note, you can only add and subtract matrices if they are the same size. And by size, I mean the row by column information. Was that Shemaya? Oh, good. I'm glad you felt that way, yeah. Very easy compared to the material we were doing before. So that's addition. Now,
Which looks like this thing.
yeah, we're gonna have to come back to that one because we need to know how to put that information in the matrix, but we can do 27. So a company makes 3 types of cable. So everybody, this is good practice. 3 types of cable. We're gonna have cable A, cable B, and cable C. Each row is going to represent one of our cables. Furthermore, we have black wires, white wires, and red wires. So we have black wires, what?
Red.
Red,
And white.
and then white.
Well, it's 3 black, 3 white, and 3 red. I don't know if you're keeping the order of the color. It's
I do want to keep the order.
black, white, red.
Oh, black, white, red. Okay. Okay. So, furthermore, they're saying, so they have all that information, and then make a 3 by 3 matrix showing this requirements. Oh, well, great. Well, that's it. We just have to show the matrix.
Oh, wow.
Yeah, so that is pretty simple, right? So that would be 3, 3, 2. Right?
1.
Oh, yeah.
Mm-hmm.
Oh, hell's bells.
Okay, so that was much more simple.
Much.
Yeah. See, now it makes me want to go back to that barge thing because it's got to be just like that. It really does. Showing the shipping costs. Make it 2 by 2.
In the answers, it seems like there's 4.
Oh, and
So
see,
it's gonna be 4.
we're gonna look at it. It even says. Oh, sorry. Go ahead. Yeah.
No.
Okay. So it even says assign the ports to the rows and assign the cities to the
tells you.
columns. So this would be port. What? Port X, port Y, just like we were starting. And then they say assign the cities to the column. So that would be city A and city B, right? And it says barges from ports X and Y went to cities A and B. So shipping costs $220 from X to A. So I'm assuming that we put a $220 right here. And then $300 from X to B, and $400 from Y to A, and $180 from Y to B. And that's it. It's just telling you what the cost is for any given particular direction that you ship. All right, how does that one feel? That feels okay? All right. Okay, we already did the cable. Folks, how would you set up number 28? And now notice that this says write this information as a 2x3 matrix. What will that look like? A 2x3.
So oak and walnut on the side.
2 rows, 3 columns.
Yeah, so probably oak and walnut are our 2 rows, right?
Yes.
And then what are our 3 columns? 8
This-
inch, 12 inch, 18 inch?
Yes.
Yeah.
Yeah. 8 inch, 12 inch, 18 inch. Okay.
I hope our tests are like this.
Oh, you like this one's much better? Yeah, the other ones were very work intensive.
And then graduate us.
Yeah. And so then what? We just put in the total number of each? So that was 47 of those, 11 of those, 40 of those, and 8.
8, 10.
And we're missing
Oh.
a 12, so no 12.
Yeah, there we go.
And 10.
Oh, sorry, 8 and 10. Yep. Now, notice now that these are just matrices. Are they augmented matrices? They're not augmented because we don't have some sort of like an answer column over here to tell us what we're actually doing with this matrix in order to actually solve something. This is just the technical equation for your X column and your Y column. There's no answer column here. Okay, so that's taking information, putting it into the matrix. Now, this particular one. Now,
Multiplying?
well, we're still in the addition section. Yeah. Notice here that this looks like a very long problem. And so you might get, oh no, like this is long. But let's just see. Carney and Dobler, they sell auto and hazard insurance. Their sales in dollars for months of July and August are given. So you'll notice that this whole matrix is July. And you can see that this is Carney. He sold 22,000 in auto and 45,000 in hazard. And this is Dobler. He sold 16,000 in auto and 27,000 in hazard. This is just the month of July.
Are we subtracting them both?
Well, let's find out what the question says. It says find a matrix that gives the increase or decrease, that is the change in sales by each salesman for each type of insurance from July to August. So we really just want to know the change. Yeah, how much it changed. So it either goes up or it goes down. So you just compare the numbers, again, cell by cell or entry by entry. So look at the upper left for Carney. It went from 22,000 to 25,000, so what's the change?
33,000.
3,000, so that would be your first entry. And then look at the upper right one. It went from 45,000 down to 44,000.
So negative
So that's a
2,000.
negative 1,000. Likewise, it went from 16,000 to 14,000.
So negative 2,000.
And then it went from 27 to 21.
So negative 6,000.
Yeah. So this matrix represents the change. Yeah, we really should have started with these sections, huh?
Yeah.
Yes.
Yeah, we were all pretty terrified by the section, the first couple. Okay, so is that the matrix that gives the increase and decrease in sales? Yes. Okay, well that's addition and subtraction. Pretty simple, right? Adding and subtracting. Multiplying is more complex, to be sure. So let's go ahead and try it. Now, these first couple are not complex. How do you solve this first one? They say let A be the matrix given. What's 2 times A? What do you think you would do?
Just multiply.
Multiply it in there.
Multiply every single term by 2. That's it. You multiply every single term by 2. So what's your final answer going to be?
Negative
6, 2, 0, 4.
Yeah, that's exactly right. This is called scalar multiplication. I put it at the top. Scalar multiplication is when you multiply every entry in a matrix by a given number.
Uh-huh.
31 is a little more exciting because it's asking us to find 3A plus B. So what would we do?
Multiply first.
Yeah, multiply this whole thing by 3, and then just add that to every entry. So let's multiply that first matrix, everything by 3. So 6, 9, 6, 15. And And then we're going to add it to the B matrix, which is 0, 4, negative 1, 6. And we add those together, term by term by term.
6, 13, 5, and 21.
Yeah. Now, on the one hand, folks, this is much easier, right? But we're really not solving much, are we?
No.
I mean, this is totally arbitrary. They're just giving us the matrices and adding them together. Are we finding a point of intersection? No, we're not really doing anything, and that's why it's so easy, because we're not really solving anything. Likewise, you can do that next one, number 32. C minus 2D. Use D by 2 and then subtract the 2. Simple. Let's keep going. This is real matrix multiplication. Real matrix multiplication is when you multiply an entire matrix times an entire matrix. Now, what do you wish matrix multiplication meant? That you would do what?
Multiply
Each term.
Multiply, 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 and it's definitely not that. Yep, so let that go from your mind. It is not that at all. Instead, what I'd like you all to do is let's go ahead and write this fairly big on your paper. So rewrite it and make it big. So negative 2, 3, 4, 2. And then negative 2, 0. And negative 1, 5. All right. You're going to need your fingers. And what you do is, with your left hand, you trace the row, and on the right hand, you trace the column, and we're going to start at the same entry. So we're starting at the upper left-hand entry. And what you're going to do is you multiply, and then you add the next product as well. So you're going to do product plus product. This is like, you know? So just first of all, practice everyone moving to the right with your left hand and down with your right hand. So everybody start in the upper left, and then you go that way and this way. So together they go like that. You're moving right with your left hand and down with your right hand. So can everybody try that?
Yes.
Are you doing it?
Yep.
Okay, so we're doing product plus product. First, product. What's negative 2 times negative 2? 4 plus 3 times negative 1? Negative 3. So that's going to be 4 plus negative 3.
Wait, what?
What?
Yeah, I'll go back. Negative 2 times negative 2 is 4. So I'm going to jot that down. 4 plus. And then 3 times negative 1,
It's
negative 3.
Oh,
And so 4 plus
Yeah.
negative 3, whatever that is, that's going to be the first entry. Okay. So we just did the first one. That gave us the first entry. Now, to get the next entry, we're going to again start moving this way with our left hand.
Yeah.
But now we're at the next column over to get the next digit, and we go down. So we're going right and down simultaneously. And it looks again like this. So negative 2 times 0 is 0. And then plus
15.
3 times 15. So that's going to be 0 plus 15.
Wait, can you do that one more time?
Yep.
Notes.
Yeah, so we're looking at this particular entry. And so it has to be this row and this column. Because after all, how do you get this entry? It has to be this row and this column.
Okay.
So
now.
it'll be from the first one will be row and the second will be column, right?
Yeah.
Okay.
Yeah. Okay, so that'll be 2 times 0 is 0, plus 3 times 5 is 15, so it's 0 plus 15. And that tells us that entry is 15. Okay, how do we get this entry? I should try asking it this way. This entry is going to be which row? This row.
Yeah.
And which column? This column. So we're going to go this row and this column. So again, we're going to move left and down at the same moment to get this entry. So 4 times 2 is, sorry, negative 8, plus 2 times negative 1, negative 2. So it's going to be negative 8 plus negative 2.
Negative 10.
Yeah. Okay, now again, let's figure out how to know what part to do. We're looking for this entry, which is this row and this column. So you do the bottom row with your left hand and the second row with your right hand. And then you're going to move across and down simultaneously. So 4 times 0, 0, 2 times 5, 10. So that's 0 plus 10. And that's 10.
How did you get the negative 10 again? I didn't.
Okay, so you want this entry right here? Thank you for asking. This entry is the bottom row, first column. Right? Bottom row, first column. So bottom row, first column.
-8,
-8,
-2.
-8 plus -2.
Yeah, that's gonna take a
Folks,
while.
it couldn't be any worse. Yeah.
Alright.
On the
Dog.
test, will we have to show all that or a calculator?
Well, you can use your calculator if you like. I mean, you
Because I
can, but
mean, you don't really show us much. I mean, once we get the hang of it, we can just.
yeah, you could type it in your calculator if you liked. Yeah. Okay, so that's matrix multiplication. Now, right now, you might be saying, well, okay. I mean, what's that good for? It's going to be good for our next method. So let's go ahead and practice one more time. Number 34. We want to multiply 3, -2,
Is it 3 times?
0. What's that?
Nothing, talk to myself. Would that be 0 and 6? -6?
Well, let's try. And again, we're going to go through and really focus on how do we know which one to do. I want the first entry, which is the first row, first column. So I point at the first row, I point at the first column, and that's going to be 3 times 0 is 0, plus -6 is -6, so it's -6. Is that what you just said, Julie?
Yeah.
That's correct. Now I want the second entry. That's the first row, second column. So first row, second column. So that'll be 3 times -2, which is -6. -2 times 6 is -12. -6 plus -12,
-18.
-18.
So we're still getting the number 3 for the top? For this, I thought it was a -2 and then -2.
Oh, not all on the top.
Yeah.
Number.
For this one, you would look at the first row, second column. So here's the first row, and here's the second column. So it'd be 3 times -2 plus -2 times 6. What are you saying, Julie?
No, I'm
You
not
got it?
sure.
Okay. Okay, this entry, second row, first column. So second row, first column, 3 times 0 plus 0 times 3.
0.
0 plus 0 is 0. This is tricky. Who's done this before?
I have, but I mean, it's been a while.
Yeah, it's been a while, right? Yeah, it's been a while.
Isn't there like a numerical value for each spot inside the matrix, like from left to right, like top on the top, like 1, 2, 3, 4?
You could call it by different things, yeah.
Like A, B.
Yeah.
Each one, then like,
Yeah, we are gonna get to that, yeah. Okay, let's do the last one. This one is the second row, second column. So we go second row, second column, 3 times -2 is -6, 0 times 6 is 0, so it's just -6. Right, that's how we multiply. So, that's matrix multiplication. What is it good for? So, let's just verify real quick, is there anything else that you can multiply? So we just did 2 by 2 by a 2 by 2. Let's clarify. What's the size of the first matrix?
2 by 2.
2 by 2. So let's go ahead and write down 2 by 2. And maybe let's just put that in like a bracket. So that's the size of the first one. What's the size of the next one?
2 by 3.
2 by 3. You can multiply this one because the middle two numbers are the same. That's the rule for matrix multiplication. The middle two numbers have to be the same.
The answer is going to be a 2 by 3.
And very good. The answer is going to be a 2 by 3 matrix. That's what's going to happen when you're done multiplying. So let's try that. If the matrices are different sizes, that's okay. But the middle numbers, if you just list them in order of their sizes, the middle two have to be the same. And the outer two numbers are going to represent the resulting size of your answer. So let's do that. I'm going to go ahead and write this down. So -1, 3, 3, 2. And then 0, 2, -2, 7. And 1, -3, 2. And what's the size of our resulting matrix?
0.
2 by 3. So that's a 2 by 3.
So, can I have a crack at the first one?
Yeah. So the first entry is the first row, first column.
So, 0. And I can't see that. And then 3.
0 plus 3 is
3.
3. Keep going, Julie.
-2 times -1 is 2. And then -9,
Yep, so 2 minus 9.
-6. -7, sorry.
7. Yeah,
I was
-7. Very
thinking-
good. Okay, last entry again. First row, third column. First row, third column.
-7, and then +6,
Yep.
so -1.
Very good. Yeah, that's how that works.
Oh, okay.
Is that okay? This is crazy town, right? It's very different, but this is how it works out if you're doing a real problem that's a word problem with actual values. Okay, so then the last one, you do get faster as you go. So that'd be 0 plus 2 is 2, and -6 plus -6 is -12, and 21 plus 4 is 25. Provided I did that correctly. Okay, and it all worked out. The middle two numbers worked, the outer two numbers tell you the size of the result, and sure enough, that's what it ended up being.
36, there's no solution, correct?
Yeah, look at number 36. What are the sizes?
2 by 3 and 2 by 2.
2 by 3 and 2 by 2. The middle two numbers are not the same, so you can't multiply them. And that's it. You just can't multiply them. You just can't. All right, now 37. Oh, good boy, I'm so excited. This is such a good problem. This is a real, genuine, interesting problem. And in fact, 37 and 38 are the same. Okay, good. This is great. All right.
Is this multiplying each of them together?
Well, yeah, that's the short of it. You just multiplied them together. But let's talk about what we're actually figuring out. Okay, so everybody, I want you to wrap your mind around the problem. Yes, as Julie said, you can just multiply the two matrices together and you're done. But let's figure out what we're doing. A company makes 3 types of chocolates: cherry chocolate, almond chocolate, and raisin chocolate. Matrix A gives the amount of ingredients in one batch. Okay. So to make cherry chocolate, you need 4 cups sugar, 6 cups chocolate, and 1 cup milk. To make almond candy, you need 5 cups of sugar, 3 cups of chocolate, and 1 cup of milk. To make raisin candy, you need 3 cups of sugar, 3 cups of chocolate, and 1 cup of milk. Now, that's all well and good. That's just the ingredients, right? How much does it cost? How much does it cost to make raisin candy? How much does it cost to make almond candy? And how much does it cost to make cherry candy? This, I believe,
Tells you the cost of the ingredients.
yeah, matrix B gives you the cost of the ingredients. So how much does sugar cost from company X? $3. How much does sugar cost from company Y? $2. How much does chocolate cost from company X? $3. Chocolate costs $4 from company Y. Milk costs $2 from company X, and milk costs $2 from company Y.
So when we multiply, we're gonna find the total cost to make cherry chocolates if we purchased it from X company, then.
Yeah, it's going to give us the particular answers. So let's try to wrap our minds then. First of all, when we multiply, does it say what order to multiply it in?
No.
It says just multiply the matrices. I wonder what order should we do it in? Matrix A, what's the size?
3 by 3.
3 by 3. What's the size of matrix B?
3 by
3 by 2. Can we multiply them in either order?
Yes.
No.
Right now we can multiply this because the middle two numbers match
Yeah.
and the result will be a 3 by 2. Could I switch them?
No.
Because
No.
it has to be AB.
Yeah, because if I switch it and multiply it this way, the middle two numbers don't match. And so you can't do it. So we have to multiply it in the order A times B. So let's do that. We'll go ahead and write down matrix A, which is 4, 6, 1, 5, 3, 1, and 3, 3, 1. And then matrix B would be 3, 2, 3, 4, and 2, 2. Okay, before we finish this problem, well, no, we're going to finish the problem because we already started, and then we just need to talk for a second about how we're going to wrap up this chapter. So, multiply. What should our final form be? 3 by 2? So that's 3 rows, 2 columns. So it'll look kind of like that. And then this is going to be a lot of multiplication. 4 times 3 is 12. 6 times 3 is 18. And then 1 times 2 is 2. That's a lot to do in your head. You'd have to keep track as you go. My final number was 32. You'll have to do each one. Now, of course, this is when using a calculator would come in really handy because you just type in the matrix, and then you multiply them. Or let's go ahead and do one more of these. So let's calculate this one. So this would be 4 times 2 is 8. Oh, there it is. Times 6 times 4 is 24. And then 1 times 2 is 2. So that's 32. That's 34. Now, what do these things represent again? Yeah, we know that the top has to represent what? Sugar, chocolate, milk, or XY?
XY.
Yeah, XY. Which again represented our costs, right? Well, really that's supplier X and that's supplier Y, but these numbers that we ended up with were costs. Yeah, and then the other side is going to represent
the different types of chocolates.
Yeah, the different types of actual chocolates. So cherry.
Is it going to be that, or is it going to be the ingredients?
Yeah, I was gonna say, is that the cost of everything?
It's matrix B gives the cost of the ingredients. It's the cost of the ingredients. That's how many ingredients. It's going to be the cost of the actual, Because we already know the cost of the ingredients. They already told us the cost of the ingredients. We don't need the cost of the ingredients. We need the cost of the chocolate. And so, there we go. So already what we found out so far is that cherry candies would cost us $32 a batch from supplier X and $34 from supplier Y. So in that particular case, we'd probably want to go with supplier X for cherry candy. And so on and so forth, we get the rest of the numbers. And it will just tell you the cost of each candy from each supplier. Okay, that would be the end of that problem. Okay, now folks, I and you, we have to think about how to conclude this chapter because technically we only got through 2.4. And 2.5 is a different method. It would probably take us, honestly, not that much longer, maybe half an hour to cover this second method, which is a good method. And then at the end, I kind of threw on a whole other type of solution that wasn't technically in the book, so we can definitely skip that. But as far as this other method, part of me wants to say, we'll do it next week, Wednesday. We'll do it Wednesday. After all, my math lab homework is not due until next week, so there's no reason why we can't just figure that or finish this on Wednesday. Now, the only problem with that is that next week we're doing chapter 17, and that's going to eat into my time in chapter 17. And then I wondered to myself, well, would we be able to finish all of chapter 17? Because then if we don't finish chapter 17, well, I have to because the next class is the test. What's that, Anna?
I don't like those.
Derivatives of big graphs, yeah. On the other hand, what we get through and understand will determine what we put on the test. If I don't have enough class time to do it with you, I'm not going to put it on the test. So, you're not going to be punished. I'm not going to be like, well, sorry, we didn't get to it. So you have to test on it anyway. So I think that's what we're going to do. We're going to save section 2.5 for next time, which means for homework tonight, what you guys should all do is go do my math lab for sections 2.1 through 2.4. And my commitment to you is that I will go onto my math lab and more closely scrutinize the problems I gave you to make sure that I'm only giving you problems like what we did in class. Because I don't want to hold you accountable to something we didn't do. So is everyone clear on what I just said?
Yes.
What did I just say?
Do 2.1 to 2.4.
And what am I going to do?
We're going to make sure that we don't have homework.
I'll go straight home tonight and I'll look at that. So that none of you get home and you're like, oh no, how do I do this one? So I'm going to go fix that. And on Wednesday, we'll do section 2.5 and then move through as much as we can in chapter 17.
Do you have the stuff that I missed from first class?
Yes, I do. Yeah, whoever needs photocopies. Now, who wants one more Starburst?
Oh, do we turn this in or off?
Oh yeah, can I have it? If you didn't already give them to me, can I have your syllabus quiz and your personal information, your student info?
Thank you.
Oh, you're welcome. Now, remember folks, please throw away your candy wrappers or else I'm blaming you. I'm saying, what? They ate candy in class? You're kidding.